Welcome to Sleepy Science Student, where we explore the cosmos, one gentle discovery at a time. Tonight, we're going on a slow, peaceful journey beyond our solar system into the vast darkness where thousands upon thousands of distant worlds orbit alien suns. We're going to talk about exoplanets, planets that circle stars other than our own sun. Worlds so far away that their light takes years, decades, even centuries to reach us. I hope this video isn't too interesting, though if it does happen to keep you awake, at least you'll be learning something fascinating about the universe's vast collection of worlds in the process. Not the worst way to spend a sleepless night, wandering among the stars from the comfort of wherever you are right now. Before we drift off into the cosmic neighborhood together, I'd love it if you gave this video a like, and maybe even subscribed if you haven't already. It really helps this sleepy little channel grow and means more curious minds can find their way here to explore the gentle mysteries of science. I'd also love to know where you're watching from and what time it is for you right now. Are you tuning in from a cozy bed in Melbourne at midnight? Or listening from a hammock in Portland at 3 in the afternoon, while the sun filters through the trees? Let me know in the comments. It's always such a joy to see the sleepy science community scattered gently across the globe, all of us wondering about the same distant worlds. Now, settle in, get comfortable, let your shoulders drop, let your breathing slow. You don't need to remember any of this. You don't need to take notes or stay alert, or memorize the names of distant star systems. Just let the words wash over you like starlight falling softly through space. And as we begin this gentle voyage beyond our solar system, remember that this video is for educational and relaxation purposes only. It's not intended as medical advice, professional astronomical guidance, or a substitute for actual space travel, though it might give you pleasantly cosmic dreams. Ready? Let's begin. Alone in the universe, the question that started it all. For thousands of years, humans have looked up at the night sky and wondered. We've wondered about the points of light scattered across the darkness like salt spilled on a black tablecloth. We've wondered if we're alone. We've wondered if, somewhere out there, among all those distant suns, other worlds orbit. Worlds with mountains and oceans, worlds with weather and seasons, worlds where, perhaps, something lives and wonders back at us. It's a question as old as consciousness itself, really. Ancient philosophers debated it. Medieval astronomers pondered it. Scientists have pursued it for generations. Are there other planets out there? And if so, what are they like? For most of human history, we could only speculate. We could imagine, we could write stories about alien worlds and create elaborate theories. But we had no way to know for certain. The stars were simply too far away, the planets too faint, the challenge too immense. It was like trying to spot a firefly next to a blazing bonfire from 1,000 miles away. Possible in theory, but practically speaking, impossible. But humans are curious creatures. We don't give up easily on our questions. We build better tools. We develop new techniques. We try and fail and try again. And slowly, gently, patiently, we learn to see what was once invisible. The first confirmed detection of a planet orbiting another sun-like star came in 1995, just 1,995. Think about that for a moment. If you're old enough to remember the mid-1990 seconds, you lived in a time when humanity didn't know for certain that planets existed beyond our solar system. The internet was just beginning to connect the world. Cell phones were becoming common, and we had no proof that our solar system wasn't unique in hosting planets. Two Swiss astronomers, Michel Mayor and Didier Queloz, were the ones who made that first confirmed discovery. They were working at the Haute-Provence Observatory in France, using a telescope and a technique that measured tiny wobbles in starlight. They were patient, they were methodical. They were, like all good scientists, prepared for disappointment. But then, they found something. A wobble in the light from a star called 51 Pegasi, about 50 light-years from Earth. The wobble suggested something was tugging on the star, pulling it gently back and forth. And the only thing that could cause that kind of motion was something with mass, something substantial, something planetary. They'd found a planet, the first exoplanet orbiting a sun-like star. They called it 51 Pegasi b, and it turned out to be nothing like anyone expected. You might think that the first exoplanet we discovered would be similar to Earth. Small, rocky, at a comfortable distance from its star. But the universe, as it often does, surprised us. 51 Pegasi b was huge, about half the mass of Jupiter, and it orbited its star incredibly closely, completing an orbit in just over 4 days. 4 days. It takes Earth 365 days to orbit the Sunday. This massive planet whipped around its star in less than a week. Scientists called it a hot Jupiter, and it baffled them. Gas giants like Jupiter in our solar system orbit far from the Sun, out where it's cold, and where they originally formed. But here was a giant planet practically skimming the surface of its star, heated to temperatures of over 1,000 degrees Celsius. It challenged everything we thought we knew about how planetary systems form and evolve. But that's the beautiful thing about discovery, isn't it? The universe doesn't conform to our expectations. It simply exists, following its own rules, waiting patiently for us to catch up with our understanding. After 1995, the floodgates opened. More astronomers started looking for exoplanets. Better techniques were developed, more sensitive. Instruments came online, and planet after planet was discovered, each one adding to our understanding, each one raising new questions. By the year 2000, we'd found about 30 exoplanets. By 2010, that number had grown to over 500. And today we know of more than 5,000 confirmed exoplanets, with thousands more candidates waiting to be verified. 5,000 worlds orbiting other stars. 5,000 examples of planetary diversity. 5,000 opportunities to wonder, what might these worlds be like? Some are scorching hot, some are frozen solid, some are rocky like Earth, some are gaseous like Jupiter. Some orbit their stars so closely they complete an orbit in hours. Others drift in the outer darkness, taking centuries to complete a single year. The variety is staggering. The possibilities, endless. And we're just getting started. We're still in the early days of exoplanet science. We're still developing our tools, refining our methods, learning to see better and farther. Every year, we find more worlds. Every year, our understanding deepens. Every year, the universe reveals a little more of its vast inventory of planets. So tonight, let's explore these distant worlds together. Let's talk about how we find them, what they're like, and what they might tell us about our place in the cosmos. Let's drift through the cosmic neighborhood, visiting alien suns and the planets that circle them. Let's wonder, softly and patiently, about the universe's remarkable collection of worlds beyond our own. Take a breath. Let your mind expand outward like ripples on a pond. We're going somewhere far away tonight, but we'll travel slowly, gently, 1 light year at a time. How do you spot a firefly next to a bonfire? Detection methods. Finding exoplanets is hard, not just difficult, not just challenging, genuinely, monumentally, almost impossibly hard. And to understand why, let's think about the scale we're dealing with here. Imagine standing in New York and trying to spot a firefly hovering next to a brilliant searchlight in Los Angeles. That firefly is billions of times dimmer than the searchlight. It's tiny, it's faint, and it's lost in the searchlight's glare. That's roughly what astronomers face when trying to detect an exoplanet next to its host star. Planets don't produce their own light. They're not stars. They shine only by reflecting the light of the suns they orbit. and compared to those suns, they're incredibly dim. Jupiter, the largest planet in our solar system, is about 1 billion times fainter than the Sunday Earth, is even dimmer, 10 billion times fainter than the Sunday, and we're trying to detect these faint worlds from distances measured in light years, across the vast emptiness of interstellar space. So how do we do it? How do we find something so small and dim against something so bright? The answer is, we get clever. We use indirect methods. We look not for the planets themselves, but for the effects they have on their stars. We watch for tiny wobbles, subtle dimmings, infinitesimal gravitational tugs. We're like detectives examining evidence at a crime scene, piecing together what happened by studying the clues left behind. Let's talk about the main detection methods, shall we? We'll start with the one that found that very first exoplanet back in 1995. The radial velocity method, watching stars wobble. Think of a star and planet as two dancers. When two dancers hold hands and spin, they don't spin around one person while the other stays still. They spin around a common center point between them. The larger dancer moves less, the smaller dancer moves more, but both are dancing. The same thing happens with stars and planets. A planet doesn't orbit a completely stationary star. Both the star and the planet orbit their common center of mass. For a star and planet, that center of mass is usually inside the star itself, but the star still wobbles slightly as the planet tugs on. Now, that wobble is tiny, absolutely minuscule. The sun wobbles by about 13 meters per second because of Jupiter's gravitational pull. 13 meters per second might sound like a lot, but remember, we're measuring this from light years away. It's like trying to measure the speed of a snail from the other side of the country. But here's where it gets clever. When a star wobbles toward us, its light shifts slightly toward the blue end of the spectrum. When it wobbles away from us, its light shifts slightly toward the red end. This is called the Doppler effect, the same effect that makes an ambulance siren sound higher pitched as it approaches and lower pitched as it moves away. By carefully measuring these tiny color shifts in a star's light shifts of just a few nanometers in wavelength, astronomers can detect the wobble, and from the wobble, they can infer the presence of a planet. They can even estimate the planet's mass and orbital period based on how big the wobble is and how quickly it repeats. This is the method that found 51 Pegasi b. This is the method that opened the door to exoplanet science. It requires patience, precise instruments, and careful analysis, but it works. Slowly, gently, reliably, it reveals worlds we cannot see directly. The transit method. Watching stars. Dim. Here's another clever trick. If a planet passes directly between us and its star, if it transits across the star's face, from our perspective, it blocks a tiny fraction of the star's light. The star dims, just slightly, for a few hours. Then the planet moves on, and the star returns to its normal brightness. This dimming is extraordinarily subtle. When Earth transits the Sun, as seen from a distant star, the Sun dims by about 0.008%. That's 0.08%. Jupiter causes a dimming of about 1%. These are tiny, tiny changes. But with sensitive enough instruments, we can measure them. The beauty of the transit method is that it's remarkably productive. If you point a telescope at a patch of sky containing thousands of stars and watch them all continuously for months or years, you can catch transits happening around many different stars. You're essentially setting up a net and waiting to see what swims into it. This is how the Kepler Space Telescope revolutionized exoplanet science. Launched in 2009, Kepler stared at a single patch of sky containing about 150,000 stars. It watched. It waited. It measured tiny dips in brightness with exquisite precision, and over its 9-year mission, it discovered more than 2,700 confirmed exoplanets and identified thousands more candidates. The transit method not only reveals that a planet exists, but also tells us its size. The amount of dimming depends on how much of the star's disk the planet blocks, which depends on the planet's diameter. A big planet causes more dimming than a small one. So from that tiny dip in brightness, we can calculate how large the planet is. Combine transit, observations with radial velocity measurements, and you get both the planet's size and its mass. And from size and mass, you can calculate density, and density tells you what the planet might be made of. Is it rocky like Earth, gaseous like Jupiter, icy like Neptune? The clues pile up, slowly painting a picture of a world we've never seen. Direct imaging, the ultimate challenge. Sometimes rarely, but sometimes we can actually take pictures of exoplanets. This is called direct imaging, and it's the most difficult detection method of all. Remember that firefly next to a searchlight. Direct imaging is like trying to photograph the firefly without being blinded by the searchlight. It requires special instruments that block out the star's light using devices called coronagraphs or star shades. These work a bit like holding your thumb up to block the sun when you're trying to look at something nearby. The star's light is blocked, creating an artificial eclipse. And in that darkness, we might spot the faint glimmer of a planet. The planets we can image directly are usually young, massive, and far from their stars. Young planets are still glowing with the heat of their formation. Massive planets are brighter than small ones. And planets far from their stars are easier to distinguish from the star's glare. But even with all these advantages, direct imaging is difficult. We've only managed to directly image a few dozen exoplanets so far, but when it works, it's magical. We're looking at actual photons that bounced off an alien world. We're seeing light that traveled across light years of space from a planet circling another sun. It's not a wobble or a dimming or an indirect measurement. It's an actual picture, however fuzzy, of another world. Gravitational microlensing. When gravity bends light. Here's a method that sounds like science fiction, but is very real. Einstein showed us that massive objects bend space itself, and light follows that bent space. So if a star with planets passes in front of a more distant star from our perspective, the closer star acts like a lens, bending and magnifying the light from the distant star. The distant star brightens temporarily as the nearer star passes by. And if the nearer star has planets, those planets cause additional little bumps in the brightening curve. By analyzing these bumps, astronomers can detect planets, sometimes even small ones like Earth. This method has found some remarkable worlds, including planets orbiting very distant stars, and even free-floating planets that don't orbit any star at all. Lonely worlds drifting through the darkness between the stars. But it has a limitation. Each microlensing event is unique and unrepeatable. The alignment that causes the lensing happens once and never again. You get one chance to observe it, and that's it. Astrometry, measuring tiny positions. There's another method worth mentioning, though it hasn't yet discovered many planets. Astrometry involves precisely measuring a star's position in the sky over time. If a planet is tugging on the star will trace a tiny circular or elliptical path in the sky as it orbits the common center of mass with its planet. This wobble is different from the radial velocity wobble. Radial velocity measures motion toward and away from us. Astrometry measures motion across our line of sight. It's measuring the star's actual position changing in the sky, which requires incredibly precise measurements. The European Space Agency's Gaia mission is designed to do exactly this, measuring the positions of over 1 billion stars with unprecedented precision. As Gaia's data accumulates, it will likely discover many planets through astrometry, adding yet another tool to our exoplanet hunting toolkit. Combining methods, building a complete picture. The real magic happens when we combine methods. A planet detected by transits can be followed up with radial velocity measurements. This gives us both size and mass, letting us calculate density. A planet detected by microlensing might later transit its star, giving us additional information. Direct imaging can confirm planets detected by other methods and tell us about their atmospheres. Each method has strengths and weaknesses. Each method is sensitive to different types of planets. Transits find planets that happen to pass in front of their stars from our perspective. Radial velocity finds massive planets that create big wobbles. Direct imaging finds young, massive planets far from their stars. Microlensing can find planets anywhere, even very far from Earth. Together, these methods let us census the galaxy's planets. They let us find tiny rocky worlds and massive gas giants. They let us discover planets close to their stars and planets far away. They let us build a statistical understanding of how common different types of planets are, how they form, and how planetary systems evolve. And all of this from tiny wobbles, subtle dimmings, and clever tricks with light and gravity. We humans are resourceful, aren't we? Faced with an impossible challenge, finding dark worlds next to brilliant stars across vast interstellar distances, we found not one solution, but many. We found ways to see the invisible. We found ways to detect the undetectable. Let's pause for a moment and appreciate that. Close your eyes if you'd like. Imagine the darkness between the stars. Imagine tiny worlds out there, orbiting alien suns, waiting patiently to be found. And then imagine human beings, here on Earth, devising these clever methods to find them, one by one, adding to our collection of known worlds, like stamps in a vast cosmic album. We're doing something remarkable, you and I. We're learning about the universe. We're discovering its secrets, and we're doing it together, gently, one planet at a time. A diverse cosmos, the unexpected variety of exoplanets. When we finally started finding exoplanets, scientists had expectations. They expected to find solar systems similar to ours, rocky planets near the star, gas giants farther out, maybe some ice worlds in the outer reaches, orderly, predictable, familiar. The universe, it turns out, had other ideas. The exoplanets we've discovered are wildly diverse, beautifully, bewilderingly, wonderfully diverse. They come in sizes and types we never imagined. They orbit their stars in ways that defy our theories. They forced us to rethink everything we thought we knew about how planetary systems form and evolve. Let's wander through this cosmic menagerie, shall we? Let's meet the different types of exoplanets, each more fascinating than the last. Take your time. There's no rush. We have worlds to explore. Hot Jupiters, the universe's first surprise. We've already mentioned hot Jupiters, those massive planets that orbit incredibly close to their stars. The first exoplanet ever discovered, 51, Pegasi b, was one of these. And at first, scientists thought it might be an anomaly, a cosmic oddity. But then we found more and more. It turns out hot Jupiters are common, or at least common enough that we've found hundreds of them. These are strange worlds. Imagine a planet as massive as Jupiter, with powerful gravity and thick atmospheres, but orbiting so close to its star that its year lasts only a few days. The temperature on the day side can exceed 2,000 degrees Celsius, hot enough to vaporize metals. The planet is tidally locked, always showing the same face to its star, just as the moon always shows the same face to Earth. On the day side, it's infernally hot. On the night side, it's somewhat cooler, but still scorching by our standards. And between these two extremes, powerful winds blow at thousands of kilometers per hour, trying to equalize the temperature difference. Clouds of vaporized minerals might rain down as tiny silicate droplets. The atmosphere could contain vaporized iron and other exotic compounds. Hot Jupiters shouldn't exist where we find them. Gas giants form far from their stars, out where it's cold enough for ice to condense. They need that ice to grow large enough to capture hydrogen and helium and become gas giants. So these planets must have formed farther out and then migrated inward, gradually spiraling closer to their stars through interactions with the disk of gas and dust they formed from. It's a bit like discovering that elephants sometimes live in trees. It challenges your basic assumptions. It makes you rethink your understanding of how things work. And that's the beauty of it. The universe is teaching us, patiently, that our theories need refining. Super-Earths, bigger than Earth, smaller than Neptune. Here's a puzzle. In our solar system, we have rocky planets like Earth that are relatively small, and we have gas giants like Neptune that are much larger, but we don't have anything in between. We don't have a planet that's, say, twice or 3 times Earth's mass. The universe, however, seems to love that size range. Many, perhaps most exoplanetary systems have planets between Earth and Neptune in size. We call them super-Earths, though that name is somewhat misleading. They're not necessarily Earth-like at all. They're just more massive than Earth and less massive than Neptune. Some super-Earths might be rocky, with thick atmospheres. Some might be ocean worlds, covered entirely in deep water. Some might be mini-Neptunes with small, rocky cores surrounded by thick envelopes of hydrogen and helium. We're still figuring out what these planets are actually like, but they appear to be one of the most common types of planets in the galaxy. Why doesn't our solar system have any super-Earths? That's an excellent question, and one that astronomers are still pondering. Perhaps Jupiter's presence prevented one from forming. Perhaps we're the anomaly. Perhaps solar systems like ours without super-Earths are actually the unusual ones. It's humbling, isn't it? Our solar system might be the weird one. Mini-Neptunes, small ice giants, related to super-Earths are mini-Neptune's planets, smaller than Neptune, but still much larger than Earth, with substantial atmospheres of hydrogen and helium. These might have rocky cores, but they're dominated by their thick, puffy atmospheres. They're like smaller versions of Uranus and Neptune, our solar system's ice giants. Many of the planets Kepler discovered fall into this category. They're common, they're diverse, and they represent a type of planet we don't have in our solar system, which means studying them teaches us about planetary possibilities we never considered. Rocky planets, Earth's cousins. Of course, we've also found rocky planets, worlds that, like Earth, Mars, Venus, and Mercury, are made primarily of rock and metal. These are harder to detect because they're smaller and don't create as large a signal in our instruments. But they're out there, orbiting other stars, solid and substantial. Some of these rocky planets orbit in their stars' habitable zones, the region where temperatures are right for liquid water to exist on the surface. These are the planets that most capture our imagination, because if there's liquid water, there might be life. But we'll come back to that topic later. For now, just know that rocky, potentially habitable planets exist. We've found them, and we're learning more about them every year. Gas giants, Jupiter's extended family. We've found plenty of Jupiter-like planets that aren't hot Jupiters. Massive gas giants that orbit their stars at more reasonable distances, where they probably formed. These are more like the Jupiter we know, though each has its own unique characteristics. Some have eccentric orbits, swinging from close to their stars to far away. Some have normal circular orbits. Some are more massive than Jupiter. Some are less massive. These distant gas giants are harder to detect than hot Jupiters because they orbit more slowly and create smaller signals in our instruments. But long-term observations have revealed many of them, filling out the galaxy's planetary census. Eccentric orbits, oval paths. Here's another surprise the universe had for us. Many exoplanets have highly eccentric orbits. In our solar system, most planets orbit the Sun in nearly circular paths, but many exoplanets orbit in stretched-out ellipses, swinging close to their stars at one point in their orbit and far away at another. This creates wild swings in temperature and radiation. A planet on an eccentric orbit might be temperate for part of its year and scorching or freezing for other parts. It's hard to imagine life evolving on such a world. But then again, life is remarkably adaptable. Perhaps organisms there have found ways to cope with the changing conditions, hibernating during extremes and thriving during moderate periods. Circumbinary planets, real life, Tatooines. Some exoplanets orbit not one star, but two. These circumbinary planets circle binary star systems, pairs of stars orbiting each other. If you stood on the surface of such a planet, you'd see two suns in the sky. It's like Tatooine from Star Wars, except real. These systems pose fascinating questions. How do planets form in binary systems? How do the two stars' gravitational influences affect planetary orbits? What would the seasons be like on such a world? With two suns contributing to the climate, we're still learning, but each discovery adds to our understanding. Free-floating planets, lonely wanderers. Perhaps the most haunting discovery is that of free-floating planets, worlds that don't orbit any star at all. They drift through interstellar space. Lonely travelers in the cosmic dark. How did they get there? Were they ejected from planetary systems by gravitational interactions? Did they form independently, like stars but too small to ignite fusion? These worlds are cold and dark, lit only by their own residual heat from taza formation and perhaps by the faint glow of distant stars. They're orphans, cast out into the void, but they're also testament to the dynamic, chaotic nature of planetary system formation. Not every world gets to keep its sun. Water worlds and lava worlds, extreme environments. Some planets might be entirely covered in ocean water worlds, with no continents, just endless seas, perhaps hundreds of kilometers deep. Others might be lava worlds, rocky planets orbiting so close to their stars that their surfaces are molten, with rivers and oceans of liquid rock glowing in the darkness. These extreme environments challenge our understanding of what a planet can be. They expand our definitions. They remind us that the universe's creativity far exceeds our imagination. The statistical picture, what we're learning. As our catalogue of exoplanets grows, patterns emerge. We're starting to understand not just individual planets, but planetary systems as a whole. We're learning that planets are common. Nearly every star has at least one planet, on average. Some stars have many planets. We've found systems with 7, 8, or more confirmed worlds. We're learning that small planets are more common than large ones. Rocky and super, Earth-sized planets outnumber gas giants. We're learning that planets can exist at almost any distance from their stars, from scorching close orbits to frigid outer reaches. And we're learning that our solar system, while not unique, is just one example among many. It's not the template for all planetary systems. It's one possibility, one outcome of the planet formation process. The universe has many templates, many outcomes, many ways of arranging matter around stars. Isn't that wonderful? The universe is not monotonous. It's not repetitive. It's endlessly creative, endlessly diverse, spinning out variations on the theme of planet in ways we're only beginning to catalogue. Take a moment to let that diversity sink in. Close your eyes, if you'd like. Imagine the variety. Hot worlds and cold ones, giant planets and tiny ones, worlds with 2 suns and worlds with none, rocky surfaces and gaseous atmospheres, circular orbits and eccentric ones. All of this exists. All of this is real. All of this is out there, waiting quietly in the darkness for us to learn about it. We're building a picture of the universe, pixel by pixel, planet by planet. And with each new world we discover, the picture becomes clearer, richer, more complete. The habitable zone, where water flows and hope resides. Now we come to one of the most captivating topics in all of exoplanet science, the habitable zone. It's sometimes called the Goldilocks zone. Not too hot, not too cold, but just right for liquid water to exist on a planet's surface. Why does water matter so much? Because life as we know it requires liquid water. Every organism on Earth, from the simplest bacterium to the largest whale, needs water to survive. Water is life's solvent, its medium, its transport system. Complex chemistry happens in water. Molecules dissolve in it, move through it, react in it. Without liquid water, life as we understand it probably can't exist. Now, this doesn't mean life absolutely requires water. Perhaps somewhere in the universe, life has evolved using a different chemistry, perhaps based on liquid methane or ammonia or something we haven't even imagined. But we don't know of any such life. We only know of water-based life. So when we search for potentially habitable worlds, we search for places where liquid water might exist. And that brings us to the habitable zone. Let's explore it together, shall we? Slowly, gently, with wonder, defining the Goldilocks zone. The habitable zone is the range of distances from a star where a planet's surface temperature could, in theory, allow liquid water to exist. Too close to the star, and water boils away, leaving a dry, desiccated world. Too far from the star, and water freezes solid, locking the poor planet in ice. But that just right distance isn't fixed. It depends on the star's temperature and brightness. Hot, bright stars have habitable zones that are far away. Cool, dim stars have habitable zones that are close in. For our Sun, the habitable zone extends roughly from Venus's orbit to Mars's orbit, though the exact boundaries are debated. Earth, of course, sits comfortably in the Sun's habitable zone. Venus is probably just inside the inner edge, where a runaway greenhouse effect boiled away any oceans it might have had. Mars is near the outer edge, cold and dry now, though it might have been warmer and wetter in the distant past, when it had a thicker atmosphere. Think of the habitable zone as a thin shell around each star, a spherical region where conditions might be just right. It's not a guarantee of habitability. A planet in the habitable zone might have no water at all, or might have a toxic atmosphere, or might be geologically dead. But it's a starting point, a place to focus our search. Factors beyond distance. What makes a world habitable? Being in the habitable zone is necessary, but not sufficient for habitability. Many other factors matter. Let's consider them one by one, building up a picture of what truly makes a world potentially livable. First, there's the planet's atmosphere. A thick atmosphere can trap heat through the greenhouse effect, warming a planet that would otherwise be frozen. A thin atmosphere provides little insulation, allowing heat to escape. Earth's atmosphere warms our planet by about 33 degrees Celsius, compared to what it would be without an atmosphere. That's the difference between a living world and a frozen one. But too much greenhouse warming is bad. Venus has a runaway greenhouse effect. Its thick atmosphere of carbon dioxide traps so much heat that the surface temperature exceeds 450 degrees Celsius, hot enough to melt lead. So the atmosphere needs to be just right. Not too thick, not too thin. Goldilocks, again. Second, there's the planet's mass. A more massive planet can hold onto its atmosphere more easily through stronger gravity. A less massive planet might lose its atmosphere to space over time, especially if it's bombarded by radiation from its star. Mars, being smaller than Earth, couldn't hold onto its atmosphere. It gradually thinned over billions of years, allowing the planet to cool and dry out. Third, there's geological activity. A geologically active planet has volcanoes that release gases into the atmosphere, replenishing what's lost to space and chemical reactions. A geologically dead planet might gradually lose its atmosphere with nothing to replace it. Earth's plate tectonics and volcanism help maintain our atmosphere and regulate our climate over geological time. Fourth, there's the planet's magnetic field. Earth's magnetic field shields us from harmful solar wind and cosmic rays. protecting our atmosphere from being stripped away. Mars lost its magnetic field early in its history, which probably contributed to the loss of its atmosphere. A habitable world likely needs either a strong magnetic field or a thick enough atmosphere to provide protection. Fifth, there's the star itself. Some types of stars are more conducive to habitability than others. Red dwarf stars, the most common type in the galaxy, are cool and dim and long-lived, but they also tend to be active, producing powerful flares that could strip away a planet's atmosphere or sterilize its surface with radiation. Sun-like stars are more stable, but they're also rarer and shorter-lived. Sixth, there's the orbital stability. A planet with an eccentric orbit swings through temperature extremes that might make life difficult. A planet with a stable, circular orbit experiences consistent conditions, which might be more conducive to the development of life. And seventh, there's the presence of moons and other planets. Jupiter, in our solar system, probably shields Earth from some asteroid and comet impacts, reducing the rate of catastrophic collisions. A large moon can stabilize a planet's axial tilt, preventing wild climate swings. Other planets in the system can influence orbits and climate in complex ways. All of these factors interact. They create a multidimensional space of habitability, where being in the right place is just one requirement among many. A potentially habitable world needs not just the right temperature, but the right mass, the right atmosphere, the right magnetic field, the right star, the right orbit, and perhaps the right neighbors. It's complicated, beautifully, wonderfully complicated, which means that while many planets might orbit in habitable zones, only a subset of those might actually be habitable. The universe is selective, demanding, exacting in its requirements for life. Optimism and caution. How common are habitable worlds? So how many potentially habitable planets are out there? This is one of the most important questions in all of astronomy, and we're starting to get answers. Based on Kepler's discoveries, astronomers estimate that about 20 to 40% of Sun-like stars have rocky planets in their habitable zones. That sounds promising, doesn't it? If true, it means there could be billions of potentially habitable worlds in our galaxy alone. But remember all those complicating factors we just discussed. Not all habitable zone planets are actually habitable. Some will lack water, some will have toxic atmospheres, some will be geologically dead, some will be bombarded by too much radiation. The fraction that are truly Earth-like, rocky, watery, temperate, protected, is probably smaller, though we don't yet know how much smaller. Still, even if only a small fraction of habitable zone planets are actually habitable, that could still mean millions or even billions of Earth-like worlds in the Milky Way. The numbers are staggering. The possibilities, breathtaking. We're not alone in hosting a habitable planet. Earth is not unique. It's one of many, perhaps one of countless, worlds where conditions might allow life to arise and thrive. That's humbling, isn't it? And exciting, and slightly vertiginous if you think about it too hard, but also comforting, in a way. We're part of something larger. We're one example of what the universe can do, and if life arose here, it might have arisen elsewhere. 2. We might not be alone after all. The red dwarf question. Are cool stars habitable? Let's talk about red dwarfs for a moment, because they're important. Red dwarfs are small, cool stars, much smaller and cooler than the Sun. They're also incredibly common. About 75% of stars in the galaxy are red dwarfs. If planets around red dwarfs can be habitable, that dramatically increases the number of potentially life-bearing worlds. But there's a problem. Red dwarfs are active. They produce powerful flares, sudden bursts of radiation that can be much more intense than solar flares from the Sun. These flares could strip away a planet's atmosphere or sterilize its surface. Any life there would need to be resilient, perhaps living underground or underwater, to shield itself from the radiation. Also, A planet in a red dwarf's habitable zone must orbit very close to its star, because red dwarfs are so dim. This close orbit means the planet is probably tidally locked, always showing the same face to its star, just like the moon always shows the same face to Earth. One side of the planet is in permanent daylight, baking under the star's light. The other side is in permanent darkness, freezing in the cold. Could life exist under such conditions? Maybe. Perhaps on the boundary between day and night, in the perpetual twilight zone, where temperatures are moderate and conditions stable. Or perhaps the planet has a thick enough atmosphere that winds distribute heat from the day side to the night side, evening out the temperature. Or perhaps life adapts, evolving to survive in extreme heat or extreme cold. We don't know yet. But the TRAPPIST-1 system, which we'll discuss in a later section, orbits a red dwarf, and it has 7 rocky planets, 3 of which are in the habitable zone. So the question of whether red dwarf planets can be habitable is not just academic, it's practical, it's immediate, it's something we can actually study with current and near-future telescopes. Beyond the habitable zone, exotic possibilities. Here's a fascinating thought. The habitable zone, as we define it, assumes a planet's heat comes from its star. But what if a planet has other heat sources? Consider Europa, one of Jupiter's moons. Europa orbits well outside the Sun's habitable zone. It should be frozen solid, and its surface is frozen. But beneath the ice, there's liquid water, an ocean, perhaps 100 kilometers deep, warmed by tidal heating. Jupiter's gravity squeezes and stretches Europa as it orbits, and that flexing generates heat, enough to keep water liquid beneath the ice. Europa might be habitable, despite being far from the Sun's habitable zone. And if Europa could be habitable, what about other icy moons in our solar system? What about icy exomoons orbiting gas giants in other systems? What about rogue planets drifting between the stars, warmed by their own residual heat and radioactive decay? Habitability might be more common and more widespread than we think. It might not be confined to a narrow zone around each star. It might exist in unexpected places, in dark oceans beneath frozen shells, in deep underground aquifers, in places we haven't even imagined yet. The universe, it seems, is generous with possibilities. It offers many potential homes for life, if we're clever enough to find them and open-minded enough to recognize them. Take a breath, let this sink in. Liquid water might exist in more places than we ever imagined. Life's possibilities might be vast, spread throughout the galaxy and beyond. We're searching for our cosmic neighbors, and the search space is larger than we thought. That's wonderful, isn't it? It means more hope, more possibilities, more reasons to keep searching. Super-Earths and mini-Neptunes, the galaxy's favorite planets. Earlier, I mentioned super-Earths and mini-Neptunes, briefly, but these planets deserve more attention, because they appear to be the most common type of planet in the galaxy. Let's spend some time with them, shall we? Let's get to know these mysterious worlds that are neither quite like Earth, nor quite like Neptune, but something in between. The size gap in our solar system. Our solar system has a curious gap. We have small, rocky planets, Mercury, Venus, Earth, and Mars. The largest of these, Earth, has a diameter of about 12,700 kilometers. Then we have giant planets, Jupiter, Saturn, Uranus, and Neptune. The smallest of these, Neptune, has a diameter of about 49,500 kilometers, but there's nothing in between. We don't have a planet with a diameter of, say, 20,000 or 30,000 kilometers. We don't have a planet that's bigger than Earth but smaller than Neptune. We jump straight from rocky planets to giants. For a long time, we assumed this was normal. We thought planetary systems naturally had this gap. But then, we started finding exoplanets, and we discovered that the galaxy loves filling that gap. Most stars have planets in that intermediate size range, planets we call super-Earths and mini-Neptunes. Why don't we have any? That's still an open question. Perhaps Jupiter's presence prevented them from forming. Perhaps they did form, but were kicked out of the solar system by gravitational interactions. Or perhaps we're the unusual ones, and most planetary systems naturally produce super-Earths and mini-Neptunes. Whatever the reason, we're missing out on what appears to be the galaxy's most popular planetary product, super-Earths, defining the category. A super-Earth is defined as a planet more massive than Earth, but less massive than Neptune. Typically, we're talking about planets with masses between 1 and 10 times Earth's mass, though definitions vary slightly. The name super-Earth is a bit misleading because it suggests these planets are like Earth, just bigger, but that's not necessarily true. A super-Earth could be rocky, like an oversized version of Earth, or it could be an icy world, or it could have a thick atmosphere of hydrogen and helium, making it more like a mini-Neptune. Size alone doesn't tell us composition. Still, some super-Earths are probably rocky. They're massive enough to hold onto substantial atmospheres through gravity, but not so massive that they necessarily accumulated thick envelopes of hydrogen and helium. They might have mountains and valleys, and perhaps oceans. They might be geologically active, with volcanoes and earthquakes. They might, in other words, be habitable. The density question: what are they made of? To figure out what a planet is made of, we need to know both its mass and its size. Mass tells us how much stuff the planet contains. Size tells us how tightly that stuff is packed. Divide mass by volume, and you get density. And density reveals composition. Earth has a density of about 5.5 grams per cubic centimetre. That density is consistent with a planet made of rock and iron, a rocky mantle surrounding an iron core. Water has a density of 1 gram per cubic centimetre. Hydrogen and helium are even less dense. When we measure the density of super-Earths, we find a wide range. Some are dense, suggesting rocky compositions. Some are less dense, suggesting they have thick atmospheres or substantial amounts of water. Some are in between. This tells us that super-Earths are diverse. Some are probably big, rocky planets. Some are probably ocean worlds, planets covered entirely in deep water, with no continents, just endless seas, perhaps hundreds of kilometers deep. Some are probably mini-Neptunes with small rocky cores and thick gaseous envelopes. It's a bit like looking at a group of people and trying to figure out what they're wearing just from their silhouettes. You can get some information, but you can't see all the details. We know super-Earths exist, and we can estimate their compositions, but we don't yet know what they're actually like. We can't see their surfaces or study their atmospheres in detail. We're still learning. The mini-Neptune problem. When does a planet become gaseous? Here's a puzzle. When does a puzzle? When does a puzzle? When does a planet? When does a planet? If you start with a rocky planet and keep adding mass, at what point does it transition from being a super-Earth to being a mini-Neptune? When does it start accumulating a thick envelope of hydrogen and helium? The answer seems to be somewhere around 1.5 to 2 times Earth's radius. Planets smaller than this can be rocky. Planets larger than this tend to have thick atmospheres. There's a gap in the size distribution of planets, a sort of no man's land where few planets exist. Planets either stay small and rocky, or they grow large enough to capture gas and become puffy mini-Neptunes. Probably because once a growing planet reaches a certain mass, its gravity becomes strong enough to start pulling in hydrogen and helium from the surrounding protoplanetary disk. The planet's growth accelerates. It balloons outward, accumulating gas faster and faster, until it either runs out of nearby gas or becomes so massive it migrates into the star or is ejected from the system. This transition point is fascinating because it divides two very different types of worlds. On one side are potentially habitable rocky planets with thin atmospheres. On the other side are gaseous mini-Neptunes with no solid surface to stand on, probably inhospitable to life as we know it. If you're looking for habitable worlds, you want super-Earths on the rocky side of this divide. You want planets that are big enough to hold onto their atmospheres, but not so big they're dominated by hydrogen and helium. You want planets in that Goldilocks range of size, composition, and location. Atmospheric escape, losing an atmosphere. Here's another complication. Over time, planets can lose their atmospheres. Ultraviolet radiation from their star heats the upper atmosphere, giving molecules enough energy to escape the planet's gravity. Stellar winds can blow away atmospheric particles. Impacts by asteroids can blast chunks of atmosphere into space. This is called atmospheric escape, and it's particularly important for planets close to their stars, where radiation is intense. A planet might start its life as a puffy mini-Neptune, but over millions or billions of years, it could lose its thick atmosphere, leaving behind a rocky core. It transitions from mini-Neptune to super-Earth through atmospheric erosion. This process might explain the gap in the size distribution. Planets either stay small and rocky, or they grow large and gaseous. Those in the middle either grow into mini-Neptunes or lose their atmospheres and become rocky super-Earths. The intermediate state is unstable. It's a bit like a mountain of snow in spring. It's either frozen solid or melting away. It doesn't stay in some intermediate slushy state for long. Planets, too, don't linger in the transitional zone between rocky and gaseous. Case study: Kepler 10c, the mega-Earth. Let's talk about a specific planet to make this more concrete. Kepler 10c is a super-Earth about 2.3 times Earth's radius and 17 times Earth's mass. That's massive, more massive than many mini-Neptunes, yet it appears to be rocky, not gaseous. When it was discovered, scientists called it a mega-Earth, and it was puzzling. How could a planet be so massive yet still rocky? Shouldn't it have accumulated a thick atmosphere of hydrogen and helium? Perhaps it formed in an environment poor in hydrogen and helium, so there was no gas to capture, or perhaps it formed later, after the protoplanetary disk had dissipated, or perhaps it lost its atmosphere through atmospheric escape, though that seems unlikely for such a massive planet with strong gravity. Kepler 10c reminds us that planets can surprise us. They don't always fit neatly into our categories. They challenge our theories. They force us to expand our understanding. The search for life on super-Earths. If rocky super-Earths exist in habitable zones, they're excellent candidates for life. They might have more surface area than Earth, providing more room for oceans and continents. They might have stronger gravity, which helps retain atmospheres. They might be geologically active, with plate tectonics that regulate climate and recycle nutrients. But stronger gravity has downsides too. It might make it harder for life to colonize land from the oceans, because lifting weight against higher gravity requires more energy. It might make it harder for large organisms to evolve, because supporting a big body in high gravity is challenging. Life on a super-Earth might tend towards smaller, more compact forms. Still, these are just speculations. We don't know what life on a super-Earth would be like, or if it exists at all, but the possibility is tantalizing, and with next-generation telescopes, we might be able to study super-Earth atmospheres, looking for biosignatures, chemical signs of life. We might find oxygen and methane in disequilibrium, suggesting biological activity. We might find other gases produced by life. The search for life is expanding beyond Earth-sized planets to include super-Earths. We're casting a wider net, looking for life wherever it might arise. And given that super-Earths are so common, they represent a significant fraction of the galaxy's potentially habitable real estate. The mini-Neptune mystery. What lies beneath? What about mini-Neptunes? These puffy planets with thick atmospheres of hydrogen and helium, probably aren't habitable in the way we usually think of habitability. You can't stand on their surfaces because they don't have solid surfaces accessible from above. Atmosphere just gets denser and denser as you descend until it transitions into a liquid or possibly a solid core. But here's an interesting thought. What if a mini Neptune has a large rocky core with water on its surface, and the hydrogen-helium atmosphere is just an outer envelope? Could there be a water world beneath the gas, a hidden ocean protected by the thick atmosphere? Could life exist there, in the dark depths, warmed by the planet's internal heat? We don't know. We can't see through those thick atmospheres, but it's possible. And possibility is what drives science. We investigate possibilities. We test hypotheses. We gradually narrow the range of uncertainty. Maybe some mini Neptunes harbour life in unexpected places. Maybe the galaxy's most common planets are also home to the galaxy's most common life. Or maybe mini Neptunes are inhospitable, their thick atmospheres crushing, and their interiors too hot. We'll find out, slowly and patiently, as we develop better tools to study these worlds. Looking ahead, characterizing super-Earths and mini-Neptunes, the James Webb Space Telescope and other next-generation instruments are beginning to study exoplanet atmospheres in detail. They can analyze the starlight that passes through a planet's atmosphere during a transit, looking for absorption lines that reveal the atmosphere's composition. For super-Earths and mini-Neptunes, this could tell us which are rocky, which are gaseous, which have water vapor, which have clouds, which have hazes. It could reveal temperatures, pressures, compositions. It could help us understand these mysterious worlds that dominate the galaxy's planetary population. We're moving from discovery to characterization. We're not just finding planets anymore. We're studying them. We're learning what they're like, what they're made of, how they behave. And each new piece of information brings us closer to understanding our place in the cosmic neighborhood. Let's pause here for a moment. Close your eyes if you'd like. Imagine a super-Earth, twice the size of our world, orbiting a distant star. Imagine mountains rising higher than Everest, pulled down by stronger gravity. Imagine oceans deeper than Earth's, with alien currents circulating in the depths. Imagine clouds drifting through a sky lit by an unfamiliar sun. These worlds exist. They're real, and we're learning about them one observation at a time. Hot Jupiters and extreme worlds, where planets defy expectations. Let's return to hot Jupiters for a bit, shall we? These strange worlds deserve more attention. They're the planets that shocked astronomers when they were first discovered. The planets that forced us to rethink our theories of planetary formation. They're worlds of extremes, of peculiar physics, of conditions unlike anything in our solar system. Settle in, get comfortable. We're about to explore some of the most extreme environments in the known universe. Don't worry, we're doing it from the safety of your bed or couch, or wherever you happen to be right now. These worlds can't hurt you. They're light years away, impossibly distant, but they can fill you with wonder, and sometimes a pleasant sense of vertigo. What makes a hot Jupiter? A hot Jupiter is a gas giant, a planet similar in size and mass to Jupiter or larger, that orbits incredibly close to its star. We're talking about orbital distances of just a few million kilometers compared to Jupiter's distance from the Sun of about 780 million kilometers. These planets complete their orbits in days rather than years. Some hot Jupiters orbit their stars in less than 24 hours. 24 hours. That's less time than it takes Earth to rotate once. The closeness to their stars means hot Jupiters are scorched. Surface temperatures, or rather, temperatures at the top of their atmospheres, can exceed 2,000 degrees Celsius. That's hotter than molten lava. Hot enough to vaporize metals like iron. Hot enough that the planet's atmosphere probably contains vaporized minerals, perhaps condensing into clouds of silicates and metallic compounds. These planets are tidally locked, meaning they always show the same face to their stars. just as the moon always shows the same face to Earth. One hemisphere is in permanent daylight, baked by the star's light. The other is in permanent darkness, though still scorching by our standards, because heat is redistributed by powerful winds. And the winds, oh, the winds. Temperature differences between the day side and night side drive winds that can reach thousands of kilometers per hour. These are not gentle breezes. These are supersonic hurricanes, eternally blowing from the hot side to the cooler side and back again in a never-ending circulation pattern. The migration mystery. How did they get there? Here's the puzzle that hot Jupiters present. They shouldn't exist where we find them. Gas giants form far from their stars, out where it's cold enough for water and other volatile compounds to freeze into ice. That ice is essential for planet formation because it provides the solid material needed for a growing planet to accumulate mass quickly enough to capture hydrogen and helium before the protoplanetary disk dissipates. Close to a star, where hot Jupiters are found, it's too hot for ice to exist, so these planets couldn't have formed where they are. They must have formed farther out and then migrated inward. How do planets migrate? There are a few mechanisms. One is interaction with the protoplanetary disk of gas and dust, from which planets form. As a planet orbits through this disk, it creates waves and disturbances in the gas. These interactions can transfer angular momentum between the planet and the disk, causing the planet to spiral inward or outward. Another mechanism is gravitational interaction with other planets. If multiple planets form in a system, they can gravitationally jostle each other, changing each other's orbits. Sometimes this leads to resonances, where planets settle into stable orbits, with simple ratios between their orbital periods. Sometimes it leads to ejections, where one planet is flung out of the system entirely, and sometimes it leads to migration, where planets swap positions or spiral toward or away from the star. A hot Jupiter might have formed as a normal gas giant, far from its star, then migrated inward over millions of years, ending up in a close orbit. Along the way, it might have disrupted any small rocky planets that were forming near the star, scattering them or swallowing them. This might explain why systems with hot Jupiters often don't have many other planets, especially close to the star. The hot Jupiter cleared them out during its migration. Studying hot Jupiter atmospheres. Windows into alien worlds. Hot Jupiters are some of the best studied exoplanets because they're relatively easy to observe. Their large size makes them produce strong transit signals. They're close. Orbits mean they transit frequently, giving us many opportunities to observe them. And their high temperatures make them bright in infrared light, making them good targets for atmospheric studies. When a hot Jupiter transits its star, some of the star's light passes through the planet's atmosphere. Different molecules in the atmosphere absorb different wavelengths of light, leaving characteristic signatures. By analyzing the starlight that passes through the atmosphere, astronomers can identify which molecules are present. We've detected water vapor, sodium, carbon monoxide, and even titanium oxide in hot Jupiter atmospheres. We've measured temperature profiles, showing how temperature changes with altitude. We've detected clouds and hazes that obscure deeper atmospheric layers. We've even, in a few cases, detected temperature differences between the day side and night side by observing the planet as it orbits, watching its brightness change as different hemispheres come into view. These observations are teaching us about atmospheric physics under extreme conditions. How do clouds form at 1,500 degrees Celsius? How does chemistry work when atoms are partially ionized by intense radiation? How do winds redistribute heat in a tidally locked atmosphere? The answers to these questions expand our understanding of planetary science. HD 189733. A. Cobalt blue world. Let me tell you about a specific hot Jupiter that's particularly fascinating. HD 189733b orbits a star about 64 light-years from Earth. It's slightly larger than Jupiter and orbits its star in just 2.2 days. Surface temperature about 1000 degrees Celsius on the night side, rising to over 1200 degrees on the day side. What makes HD 189733b remarkable is its color. Observations suggest it's cobalt blue, a deep, rich blue similar to Earth's color as seen from space. But the similarity ends there. Earth is blue because of its oceans. HD 189733b is blue because its atmosphere contains silicate particles that scatter blue light. Those silicate particles, essentially tiny grains of sand, are blown around by winds, reaching 7,000 kilometers per hour. If you could somehow stand on HD 189733b, you can't, because it's a gas giant with no solid surface. You'd be sandblasted by supersonic winds, carrying glowing hot grains of silicate. It would be unimaginably hostile. But from a distance, from the cold darkness of space, it's beautiful, a jewel of a planet, glowing blue against the black. WASP-12b, the doomed planet. Here's another extreme world. WASP-12b is a hot Jupiter, about 1.4 times Jupiter's mass, orbiting a sun-like star about 1,400 light-years away. It orbits in just 26 hours, so close to its star that it's being torn apart. The star's gravity is pulling WASP-12b into an egg shape, stretching it. The planet is overflowing, its Roche-lobe, the region within which it can hold itself together gravitationally. Material is streaming off the planet and onto the star. WASP-12b is being devoured, slowly consumed by its own sun. Astronomers estimate that WASP-12b will be completely destroyed within about 10 million years. That sounds like a long time, but in astronomical terms, it's the blink of an eye. This planet is doomed. It won't be here forever. It's a reminder that planetary systems are dynamic, evolving, sometimes violent places. Not every world lasts for billions of years. Some are transient, ephemeral, like mayflies in the cosmic timescale. Kelt 9b, the hottest known planet. And then there's Kelt 9b, the current record holder for hottest known exoplanet. It orbits a massive, hot star about 670 light-years away. The planet's dayside temperature exceeds 4,300 degrees Celsius. That's hotter than some small stars. That's hot enough that molecules break apart into individual atoms. Kelt 9b's atmosphere probably doesn't contain water vapor or carbon dioxide, or any of the complex molecules we're familiar with. It's so hot that most molecules dissociate. Iron and titanium vaporize and exist as individual atoms. The planet's atmosphere is more like a star's photosphere than a planet's atmosphere. It's hard to even call Kelt 9b a gas giant in the traditional sense. It's more like a ball of plasma, glowing with its own heat, blurring the line between planet and star. It challenges our definitions. It pushes the boundaries of what we consider a planet. Ultra-short period planets. Even closer. If hot Jupiters orbit their stars in days, ultra-short period planets orbit in hours. These are small, rocky planets that orbit so close to their stars that their years last less than a day. Some orbit in just a few hours. At such close distances, these planets are tidally locked and intensely heated. The day side might be molten rock, glowing like embers. The night side is cooler, but still far too hot for any familiar form of life. These worlds probably don't have atmospheres. Any atmosphere would be stripped away by the intense radiation and would evaporate off the hot surface. Why do these planets exist so close to their stars? How did they get there without being destroyed? They might be the remnants of larger planets that migrated inward and then evaporated, leaving only their rocky cores. Or they might have formed through unusual processes we don't yet understand. They're curiosities, extreme examples of planetary possibilities. They remind us that planets can exist in conditions that seem impossible, that the universe's creativity extends even to the most hostile environments. What hot Jupiters teach us? Hot Jupiters teach us about planetary migration. They teach us that planetary systems are dynamic, that planets don't necessarily stay where they form. They teach us about atmospheric physics under extreme conditions. They teach us about the diversity of exoplanets and the importance of not assuming that other planetary systems will resemble our own. They also teach us humility. We thought we understood how planetary systems work based on our solar system. Then we found hot Jupiters, and we had to revise our theories. We're still revising. We're still learning. The universe is a patient teacher, and we're diligent students, gradually improving our understanding, one discovery at a time. Close your eyes for a moment. Imagine a gas giant, massive and blue, whipping around its star in just a few days. Imagine supersonic winds and vaporized metals, and temperatures that would melt rock. Imagine the sheer extremity of such a place, and then feel grateful that you're here, on Earth, in a temperate environment where water flows and life thrives. We're lucky, in a way. We inhabit a gentle world, but it's fascinating to know that harsh worlds exist too, that the universe contains multitudes. The Trappist, one system, 7 worlds, one small star. Now we come to one of the most exciting exoplanet discoveries of recent years, the TRAPPIST-1 system. This is a system that captured imaginations around the world, that made headlines, that gave us hope of finding life beyond Earth. Let's explore it together, gently and thoroughly. Get comfortable. Maybe pull your blanket a little closer. We're going to visit 7 worlds orbiting a tiny star. Worlds that might harbor life. Discovering TRAPPIST-1, a Belgian telescope, and a Belgian beer. The story begins with a small robotic telescope in Chile, called TRAPPIST, which stands for Terran-Sighting Planets, and Planets Imals. Small telescope. It's named after Trappist beer, because the telescope is Belgian, and Belgians take their beer seriously. Sometimes, scientists have a sense of humor. In 2016, astronomers using TRAPPIST announced the discovery of 3 planets orbiting a small, cool star, about 40 light-years from Earth. The star itself, now called TRAPPIST-1, is an ultra-cool dwarf star, much smaller and cooler than the Sun. It's only slightly larger than Jupiter, though much more massive. It's one of the smallest stars capable of sustaining nuclear fusion in its core. 3 planets were exciting enough. But then, with additional observations using other telescopes including the Spitzer Space Telescope, astronomers found more planets, and more. By early 2017, the count was up to 7 Earth-sized rocky planets orbiting a single star. 7 worlds packed into orbits closer than Mercury is to the Sun. 7 opportunities to study potentially habitable worlds. The scientific community was thrilled. The public was captivated. Here was a system we could actually study, a system with multiple planets that transit their star, a system where we might be able to detect signs of life with upcoming telescopes. The system's architecture, compact and resonant. The TRAPPIST-1 system is remarkably compact. All 7 planets orbit closer to their star than Mercury orbits the Sun. The innermost planet, TRAPPIST-1b, orbits in just 1.5 days. The outermost, TRAPPIST-1 hour, orbits in about 20 days. If the entire system were overlaid on our solar system, it would fit inside Mercury's orbit, with room to spare. This compactness is possible because TRAPPIST-1 is so small and cool. Its habitable zone is correspondingly close in. Planets that would be scorched to cinders if they orbited the Sun can be temperate around TRAPPIST-1. But compactness creates challenges. 7 planets orbiting so close to each other means they gravitationally interact. They pull on each other. They perturb each other's orbits. In most systems, such close packing would be unstable. The planets would crash into each other, or be ejected from the system. So how does TRAPPIST-1 remain stable? The answer is resonance. The planet's orbital periods are related by simple ratios. For every orbit TRAPPIST-1c makes, TRAPPIST-1b makes almost exactly 1.6 orbits. For every orbit TRAPPIST-1d makes, TRAPPIST-1c makes 1.5 orbits. These resonances stabilize the orbits, locking the planets into a cosmic dance where they return to the same relative positions over and over. It's a bit like ice skaters holding hands and spinning, their motion coordinated. The resonances keep the TRAPPIST-1 planets from colliding or drifting apart. They create a stable, albeit tightly packed, system. The planets. They range from about 0.8 to 1.1 times Earth's diameter. They're all rocky, or at least mostly rocky, based on their masses and sizes. They're not gas giants or icy worlds. They're terrestrial planets like Earth, Venus, and Mars. This is exciting because rocky planets are where we expect to find life. Gas giants don't have solid surfaces to stand on. Icy worlds, unless they have subsurface oceans, are frozen and inhospitable. But rocky planets in habitable zones, they're prime real estate for life. 3 of the TRAPPIST-1 planets, TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1 orbit in the habitable zone. They're at distances where temperatures could, in theory, allow liquid water to exist on their surfaces. The other 4 are either too close, TRAPPIST-1b, 1c, and 1d, or too far, TRAPPIST, 1 hour, to be comfortably habitable, though there are caveats and complications, as there always are. The challenge: red dwarf radiation. But there's a problem. TRAPPIST-1 is a red dwarf, and red dwarfs can be harsh environments for planets. They're active stars, prone to flares, sudden bursts of radiation that can be much more powerful than solar flares from the Sunday. These flares emit ultraviolet and X-ray radiation that can strip away a planet's atmosphere and sterilize its surface. The TRAPPIST-1 planets orbit so close to their star that they're bathed in this radiation. They're also likely tidally locked, always showing the same face to their star. One hemisphere is in perpetual daylight, heated by the star's light. The other is in perpetual darkness, never seeing the star at all. Could life exist under such conditions? It's hard to say. Perhaps the planets have thick atmospheres that protect them from radiation. Perhaps life has adapted, living underground or underwater. Perhaps the dark side of each planet, shielded from the star's direct light and radiation, provides a refuge. Or perhaps the planets are barren, their atmospheres long since stripped away by flares and radiation, their surfaces lifeless. We don't know yet. We're gathering clues, but the picture isn't complete. Atmospheric studies. What the James Webb Telescope might reveal. The James Webb Space Telescope, JWST, has begun studying the TRAPPIST-1 planet's atmospheres. By observing the planets as they transit their star, JWST can analyze the starlight that passes through their atmospheres, looking for absorption lines that reveal atmospheric composition. Early results have been somewhat disappointing. Observations of TRAPPIST-1b, the innermost planet, suggest it might not have a substantial atmosphere, or at least not one thick enough to detect easily. But TRAPPIST-1b is too close to its star to be habitable anyway. The real question is, what JWST will find for the planets in the habitable zone. If those planets have atmospheres, JWST might detect water vapor, carbon dioxide, methane, oxygen, and other gases. It might reveal temperatures, pressures, and weather patterns. It might even, if we're incredibly lucky, detect biosignatures, chemical signs of life. Imagine that for a moment. Imagine detecting oxygen and methane together in a planet's atmosphere, a combination that suggests life is actively producing these gases. Imagine the headlines. Imagine the shift in perspective that would come from knowing, with reasonable confidence, that life exists somewhere other than Earth. It's possible, not certain, but possible, and possibility is enough to drive the search. What would life on TRAPPIST-1 worlds be like? If life exists on any TRAPPIST-1 planet, what would it be like? Let's speculate. Gently and cautiously, acknowledging that this is all guesswork. First, consider the light. TRAPPIST-1 is a cool star, emitting most of its light in the infrared. Visible light is dimmer. The sky, if you stood on one of these planets, would be a deep orange-red, not blue like Earth's sky. The star itself would appear huge. TRAPPIST-1 is so small that from its planets it would look much larger in the sky than the sun does from Earth, despite being much cooler. Plants on Earth use photosynthesis to convert sunlight into energy, and they're optimized for the sun's spectrum. Plants on a TRAPPIST-1 world might use different pigments to capture the infrared light that's abundant. They might not be green, they might be black, to absorb as much light as possible, or red, or some other color our eyes have never seen in vegetation. If the planet is tidally locked, life might concentrate in the twilight zone between the day and night sides, where temperatures are moderate. Or perhaps life exists on the day side in hot springs, or on the night side around volcanic vents, wherever conditions are tolerable. Life might be simple microbes adapted to harsh radiation and extremes of temperature. Or life might be complex organisms with sophisticated strategies to shield themselves from radiation, perhaps living in caves or deep water, or beneath layers of regolith. We have no idea. But the possibility that we might find out, that we might actually detect signs of life on another world in our lifetimes, is exhilarating. The view from TRAPPIST-1, a crowded sky. Here's a delightful thought. If you stood on one of the TRAPPIST-1 planets, you'd be able to see the other planets in the sky, not as points of light, like we see Venus and Mars from Earth, but as disks, visible and obvious even to the naked eye. The planets orbit so close to each other that they'd appear larger in each other's skies than the Moon appears from Earth. TRAPPIST-1e, standing on TRAPPIST-1f, would be a prominent feature in the sky, perhaps with visible cloud patterns and surface features. During a transit, when one planet passes in front of another, from your perspective, you'd see a dark disk sliding across the face of a nearby world. It would be a crowded, busy sky, full of neighboring worlds. If life exists on multiple TRAPPIST-1 planets, those civilizations, if they advance to a stage where they can observe the sky, would know immediately that other worlds exist. They'd see them, right there, close and obvious. They wouldn't need telescopes to know they're not alone in their system. It's a romantic thought, a system where worlds are neighbors, where the sky is full of sisters. Whether or not life exists there, it's a beautiful image. Hope and patience, the long view. The TRAPPIST-1 system reminds us to be both hopeful and patient. It's an excellent target for the search for life. It's nearby, astronomically speaking. It has multiple potentially habitable planets. It's conducive to atmospheric studies because the planets transit frequently and the star is small, making atmospheric signals easier to detect. But we won't have answers immediately. Science takes time. We need more observations, better instruments, careful analysis. We need to rule out false positives and consider alternative explanations. We need to be rigorous and skeptical and patient. The universe will reveal its secrets when it's ready, on its own timeline. We can't rush it. We can only observe, analyze, wonder, and wait. So let's do that. Let's wait patiently for more data from JWST and other telescopes. Let's keep studying the TRAPPIST-1 system. Let's nurture our hope that somewhere among those 7 worlds, life might exist. waiting quietly to be discovered. Take a breath. Let yourself feel the wonder of it. 7 worlds, each a complex system of rock and possibly water and perhaps atmosphere. 7 chances for life. 7 opportunities to discover that we're not alone. That's worth waiting for, isn't it? The search for Earth. 2. Finding a twin. All of exoplanet science, in a way, is leading toward one goal: finding Earth 2, a planet like ours, orbiting a star like our Sun, at a distance like our distance, with liquid water on its surface, and perhaps life in its oceans or on its continents, a true twin of Earth, a second pale blue dot in the cosmic ocean. We haven't found it yet, but we're getting close. Let's talk about that search, shall we? Let's explore what it means to find another Earth and why it matters. Defining Earth 2. What are we looking for? When we say Earth 2, what do we mean exactly? Different astronomers have different definitions, but generally, we're looking for a planet that meets several criteria. First, it should be similar in size to Earth. Not too much bigger, not much smaller. Let's say between 0.8 and 1.5 times Earth's radius. This size range suggests a rocky planet that can hold on to an atmosphere, but isn't so massive it becomes a mini Neptune. Second, it should orbit in the habitable zone of its star. The planet's surface temperature should allow liquid water to exist, which probably means temperatures between about 0 and 100 degrees Celsius, though there's flexibility depending on atmospheric pressure. Third, it should orbit a Sun-like star, a G-type star, similar in mass, temperature, and brightness to our Sunday. This is partly because Sun-like stars are stable and long-lived, giving life time to evolve, and it's partly because we want a true analogue of Earth, and Earth orbits a G-type star. Fourth, ideally, it should have an orbital period similar to Earth's, somewhere between, say, 200 and 500 days. This ensures the planet is at the right distance from its star, not too close and not too far. And fifth, if we're lucky, it might show signs of habitability or even life, an atmosphere with water vapor, oxygen, or other biosignatures. Finding a planet that meets all these criteria is hard. Each criterion narrows the search. Each requirement makes the target more specific and harder to find. But that's the goal, to find a planet so similar to Earth that we can look at it and say, that could be our twin, Proxima Centauri, b, close but different. The closest known exoplanet to Earth is Proxima Centauri b, orbiting Proxima Centauri, the nearest star to our Sunday. It's only about 4.2 light-years away, close by astronomical standards, though still so far that the fastest spacecraft ever built would take tens of thousands of years to reach it. Proxima Centauri b is intriguing. It's similar in mass to Earth, and it orbits in its star's habitable zone. On paper, it's a good candidate for habitability, but Proxima Centauri is a red dwarf, not a Sun-like star. It's cooler, smaller, and more active than the Sunday. Proxima Centauri b orbits very close to its star, completing an orbit in just 11 days, and it's probably tidally locked. So while Proxima Centauri b might be habitable, it's not Earth 2. It's more like Earth 0.8, similar in some ways, but different in important respects. It orbits a different type of star, in a different kind of orbit, under different conditions. Still, it's close, and that makes it a high-priority target for future studies. If we could send a probe there, a big if, requiring technology we don't yet have, it would be our first destination in the search for life beyond our solar system. Kepler 452b, Earth's older cousin. In 2015, NASA announced the discovery of Kepler 452b, dubbed Earth's older cousin. It orbits a G-type star similar to the Sun, at a distance that puts it squarely in the habitable zone. Its orbital period is 385 days. remarkably close to Earth's 365 days. Its size is about 1.6 times Earth's radius, which is larger than ideal, but still within the range where the planet could be rocky. If Kepler 452b is rocky, it's a good candidate for Earth too. It orbits a Sun-like star at an Earth-like distance with an Earth-like year. The star is older than the Sun, about 6 billion years old, compared to the Sun's 4.6 billion years. So if life evolved on Kepler 452b, it's had more time to develop than life on Earth. But there's a catch. Kepler 452b is about 1,400 light-years away. That's far too distant for detailed study with current technology. We know it exists, and we know its basic properties, but we can't study its atmosphere or look for signs of life. It's tantalizing, but frustratingly out of reach. Kepler 186, the first Earth-sized planet in a habitable zone. Kepler 186 was the first Earth-sized planet discovered in the habitable zone of another star. Announced in 2014, it was a milestone. It proved that Earth-sized planets in habitable zones exist. However, Kepler 186f orbits a red dwarf, not a Sun-like star, so like Proxima Centauri b. It's not a true analogue of Earth. It's close, but not quite right. The lesson from these discoveries is clear. Finding Earth 2 is hard, because we have to get multiple things right simultaneously. Size, check. Habitable, zone, check. Sun-like star, maybe. Accessible for study, rarely. We need all the pieces to come together, and that takes time and luck. The challenge: Sun-like stars and long periods. One of the biggest challenges in finding Earth 2 is that planets in year-long orbits around Sun-like stars transit infrequently. Earth transits the Sun as seen from a distant star once per year. If you're watching from afar, you need to observe for at least 2 transits to confirm that what you're seeing is a planet. That means observing for at least 2 years, possibly 3 or more to be certain. The Kepler mission observed its field of stars for about 4 years. That was long enough to detect multiple transits of planets with orbital periods up to about a year or slightly longer. But planets with longer periods, planets orbiting farther from their stars, weren't observable long enough to confirm. This is why we've found more planets with short periods than long ones. It's an observational bias. We can find planets that transit every few days or weeks much more easily than planets that transit once a year or less. Future missions, like the European Space Agency's Plato, Planetary Transits and Oscillations of Stars mission, are designed to observe for longer periods, allowing detection of planets in longer orbits. Plato will watch its target stars for at least 2 years, potentially longer, increasing the chances of finding true Earth analogues. The TESS mission, surveying the whole sky. NASA's Transiting Exoplanets Survey satellite, TESS, is surveying the entire sky, looking for transiting planets around bright, nearby stars. Unlike Kepler, which stared at one patch of sky, TESS is scanning broadly, covering much more area, but with less sensitivity to small, distant planets. TESS is finding many planets, including some in habitable zones, but most of the planets, TESS finds orbit red dwarfs, because red dwarfs are common and their habitable zones are close in, making planets easier to detect. Finding Earth 2 around a Sun-like star remains elusive. Still, TESS is building our catalogue of nearby exoplanets. These planets will be prime targets for follow-up studies with JWST and other telescopes. We're assembling a list of worlds to investigate more closely. Worlds that might harbour life. Worlds that might someday be destinations for robotic or even human explorers. The importance of finding Earth 2. Why does finding Earth 2 matter so much? Partly it's about understanding our place in the universe. Is Earth unique, or are Earth-like planets common? If we find many worlds like ours, it suggests that the conditions that gave rise to life might be common too. It increases the likelihood that life exists elsewhere. And partly, it's about hope. Finding another Earth would give us a target, a destination, a goal, even if we can't reach it with current technology. Knowing it's there would inspire us to develop the technology that could. It would be a light in the darkness, a beacon drawing us forward. And partly, it's about perspective. Looking at Earth from space, the famous pale blue dot photo taken by Voyager 1 gave humanity a sense of our fragility and interconnectedness. Finding another pale blue dot would expand that perspective. We'd see ourselves as part of a community of worlds, not alone, but part of something larger, the future. Direct imaging of Earth 2. The ultimate goal is not just to find Earth 2, but to directly image it, to take a photograph of another Earth-like planet, to see it as a pale blue or greenish dot, to analyze its spectrum and detect signs of life. This requires technology we don't yet have. We need space-based telescopes with enormous mirrors, or arrays of telescopes working together. We need starshades or coronagraphs that can block out the star's light completely, allowing us to see the faint planet beside it. We need years of observation and careful analysis, but it's possible. NASA has proposed several concepts for such a mission. The Habitable Exoplanet Observatory, HAB-X, and the Large UV, Optical, IR Surveyor, LUVOIR, were two such concepts. Though not yet funded, they represent the direction of future exoplanet science, direct observation and characterization of potentially habitable worlds. Imagine that moment, the first photograph of another Earth-like world, a blue or green dot on a black background, 10 or 20 or 50 light-years away. Imagine analyzing its light and detecting oxygen and water vapor and methane in just the right proportions to suggest life. Imagine knowing, with high confidence, that life exists out there, that we're not alone. That moment might come in our lifetimes, or it might take another generation or two, but it's coming, slowly, patiently, inevitably. We're moving toward that discovery. Patience and wonder, the twin virtues. The search for Earth 2 requires patience. We can't rush it. We need better instruments, more observations, longer time baselines. We need to avoid false positives and premature announcements. We need to be rigorous and careful and thorough, but the search also requires wonder. We need to keep looking up, keep searching, keep asking questions. We need to maintain our curiosity and our hope. We need to believe that the search is worthwhile, that finding another Earth matters, that understanding our place in the cosmos is one of humanity's great endeavors. So, let's be patient. Let's wait for the data. Let's support the missions and the telescopes and the scientists doing this work. And let's wonder. Let's imagine what it would be like to find another Earth, to know that life might exist there, to see ourselves reflected in another world's oceans and continents. Close your eyes, if you'd like. Imagine a planet orbiting a distant sun, with clouds drifting across its surface and water glinting in the light. Imagine calling it Earth 2, knowing it's not Earth, but something wonderfully similar. Imagine the moment when we confirm that life exists there, when we know for certain we're not alone. That moment is coming. We just need to wait for it, patiently and hopefully. Exomoons and rings, the small stuff we're starting to see. So far, we've talked mostly about planets, but planets aren't the only objects in planetary systems. There are also moons, rings, asteroids, comets, and who knows what else. Let's spend some time talking about the smaller objects, shall we? Particularly exomoons, moons orbiting exoplanets and rings. Get comfortable. Maybe adjust your pillow. We're going to explore the universe's smaller bodies, the supporting cast in the drama of planetary systems. The challenge of finding exomoons. Finding exoplanets is hard. Finding exomoons is even harder. Moons are smaller than planets, which means they produce weaker signals. They orbit planets rather than stars, which complicates the detection, and their presence creates complex gravitational interactions that can obscure their signals or create false positives. But we're trying. We're developing techniques, and slowly, we're starting to see hints of exomoons in the data. Detection methods, transit variations. One way to find exomoons is through transit timing variations. If a planet orbits alone, it transits its star at regular intervals. But if the planet has a moon, the moon's gravity tugs on the planet, causing the planet to wobble slightly. This wobble changes the precise timing of the transits. By carefully measuring transit times, astronomers can detect the presence of a moon. Another method is transit duration variations. A planet with a moon doesn't have a fixed position. It orbits the common center of mass with its moon. This causes the planet's path across the star's disk to vary slightly from orbit to orbit, changing how long the transit lasts. Again, careful measurements can reveal this variation. And a third method is direct detection of the moon's own transit. If a moon is large enough and orbits at the right distance from its planet, it might cause a secondary dip in the star's light when it transits. Detecting this dip requires exquisite precision and favorable geometry, but it's possible. Kepler 1625 b/I, the first exomoon candidate. In 2018, astronomers announced the possible detection of an exomoon orbiting a planet called Kepler 1625b. The moon, if it exists, would be about the size of Neptune, orbiting a Jupiter-sized planet about 8,000 light-years from Earth. The evidence came from transit timing and duration variations, as well as a possible secondary dip in brightness that could be the moon's own transit. But the detection is tentative. Other astronomers have analyzed the data and suggested that the signal could be due to instrumental noise or stellar activity rather than a moon. So as of now, we can't say with certainty that Kepler 1625b/I exists. It's a candidate, a possibility, a tantalizing hint, but we need more observations and better data to confirm or refute it. Why exomoons matter: habitability and diversity. If exomoons exist, and they almost certainly do, given that moons are common in our solar system, they add yet another dimension to planetary diversity. A moon could potentially be habitable even if its planet isn't. Consider Europa and Enceladus, moons of Jupiter and Saturn, which probably have subsurface oceans beneath their icy shells. They're not habitable on their surfaces, but life might exist in their hidden oceans. Now imagine an exomoon orbiting a gas giant in the habitable zone of a distant star. The moon could be rocky, with a temperate climate, liquid water on its surface, and perhaps life. The planet itself, being a gas giant, wouldn't be habitable, but its moon could be. This expands the number of potentially habitable worlds. We're not limited to planets alone, moons count too, and since gas giants can exist in habitable zones, their moons become interesting targets for the search for life. Rings, faint and fragile. Rings are even harder to detect than moons. They're thin, faint, and don't produce strong signals, but we've seen hints of rings around some exoplanets, based on unusual dimming patterns during transits. Saturn's rings, as seen from a distant star, would cause a faint, extended dimming before and after Saturn transited, as the rings blocked some of the star's light. By looking for similar patterns around exoplanets, astronomers can infer the presence of rings. One candidate is a young planet, or brown dwarf, called J1407b, which may have a ring system much larger and more massive than Saturn's. The rings, if they exist, extend out to dozens of times the radius of Saturn's rings. They might be in the process of forming moons, accreting material into larger bodies that will eventually become satellites. Rings are transient features. They're constantly losing material, either to the planet's atmosphere or to space. Moons form from rings over time. So a planet with rings is a snapshot of a dynamic process, a system still evolving and changing. The diversity of moons. What might exomoons be like? Our solar system's moons are incredibly diverse. Earth's moon is large and rocky, probably formed by a giant impact. Mars has 2 tiny, irregularly shaped moons that might be captured asteroids. Jupiter has dozens of moons, including massive Ganymede, larger than Mercury, and volcanic Io. Saturn has Titan, with a thick atmosphere and liquid hydrocarbon lakes, and Enceladus, with geysers erupting from a subsurface ocean. Exomoons are probably just as diverse. Some might be rocky, some icy, some a mixture. Some might have atmospheres, others none. Some might be geologically active, others dead. Some might be tidally locked to their planets, always showing the same face, while others might rotate freely. And some, just maybe, might harbour life. If a moon has liquid water, a heat source, whether from the star, reflected light, or tidal heating, and the right chemistry, life might arise. It might be simple microbial, living in subsurface oceans or hydrothermal vents, but it might exist. The possibility of life on exomoons adds yet another layer of complexity and wonder to the search for life beyond Earth. We're not just looking at planets anymore. We're looking at entire systems, with all their complexity and diversity, Trojan planets and horseshoe orbits, exotic configurations. Beyond moons and rings, there are other exotic configurations worth mentioning. Trojan planets are planets that share an orbit with another planet, sitting at stable points called Lagrange points, 60 degrees ahead of or behind the other planet. We have Trojan asteroids in our solar system, sharing Jupiter's orbit, but no Trojan planets. Yet, they could exist around other stars. Horseshoe orbits are another exotic configuration, where 2 objects orbit a star at nearly the same distance, periodically approaching and receding from each other in a horseshoe-shaped pattern. Again, we don't have planets in horseshoe orbits in our solar system, but the configuration is dynamically stable under certain conditions. These exotic arrangements remind us that planetary systems can be configured in ways we haven't imagined. Nature is more creative than our theories. The universe delights in surprising us. The future. Better telescopes, better data. As our telescopes improve, we'll detect more exomoons and rings. We'll characterize them, studying their sizes, masses, compositions, and orbits. We'll add them to our growing catalogue of worlds. And perhaps, one day, we'll detect a truly Earth-like exomoon, a rocky world orbiting a giant planet in a habitable zone, with liquid water on its surface and signs of life in its atmosphere. That would be remarkable, wouldn't it? A habitable moon, a world that's both a satellite and a home. The universe has already shown us hot Jupiters, super-Earths, mini-Neptunes, circumbinary planets, free-floating worlds, and 7 planets orbiting a tiny star. It's shown us diversity beyond anything we imagined. So why not habitable moons? Why not rings of incredible size? Why not configurations and possibilities we haven't even conceived of yet? Let's remain open to surprise. Let's keep our expectations flexible. Let's let the universe teach us, patiently and gently, about all the ways matter can organize itself around stars. Take a breath. Close your eyes if it helps. Imagine a moon, large and rocky, orbiting a gas giant. Imagine looking up from that moon's surface and seeing the giant planet filling the sky, its bands of clouds slowly churning. Imagine two sunrises as the star appears over the planet's limb, painting the landscape in unfamiliar colors. Imagine life there, adapted to the strange rhythm of days and eclipses. It's possible, and possibility is enough to keep us searching. Characterization. Reading the chemical signatures of distant worlds. We've talked about finding exoplanets and categorizing them by size and orbit, but now we're moving to a new phase, characterizing them. We want to know what they're made of, what their atmospheres contain, what their surfaces are like. We want to read their chemical signatures and understand their climates. We want to know these worlds as more than just statistical data points. We want to know them as places. Let's explore how we do this, shall we? Slowly, carefully, with appreciation for the ingenuity required. Spectroscopy, the key to understanding. The tool that makes atmospheric characterization possible is spectroscopy, the analysis of light split into its component wavelengths. Different molecules absorb and emit light at specific wavelengths, creating characteristic patterns called spectral lines. By examining these patterns, we can determine which molecules are present. It's a bit like identifying a person by their voice print. Each molecule has a unique spectral signature. Water vapor absorbs light at certain infrared wavelengths. Carbon dioxide absorbs at different wavelengths. Methane has its own signature, as do oxygen, ozone, ammonia, and countless other compounds. When starlight passes through an exoplanet's atmosphere during a transit, some wavelengths are absorbed by molecules in the atmosphere. By comparing the star's spectrum when the planet is transiting to its spectrum when the planet is not transiting, we can identify which wavelengths are being absorbed and, from that, which molecules are present. It sounds simple. In practice, it's fiendishly difficult. The signals are tiny. The atmospheres are thin. The planets are far away. We're trying to detect the faint fingerprints of molecules in the atmospheres of worlds light years distant. It's like trying to identify a person's voice print in a crowded stadium from a mile away. But we're doing it. We're succeeding. And the results are remarkable. Early successes. Detecting sodium and water vapor. The first atmospheric detections on exoplanets came in the early 2000s. Astronomers detected sodium in the atmosphere of a hot Jupiter, confirming that spectroscopy could indeed reveal atmospheric composition. Later, water vapor was detected, then carbon monoxide, hydrogen, and other compounds. These early detections were validation. They showed that the technique worked, that we could learn about exoplanet atmospheres remotely. They opened the door to a new era of exoplanet science. The James Webb Space Telescope, a game changer. The launch of the James Webb Space Telescope in 2021 revolutionized atmospheric characterization. JWST is an infrared telescope, and many important molecules have strong absorption features in the infrared. It's also incredibly sensitive, able to detect faint signals that previous telescopes couldn't. JWST has already studied dozens of exoplanet atmospheres. It's detected water vapor, carbon dioxide, methane, and other molecules. It's measured temperatures and pressures. It's identified clouds and hazes that obscure deeper atmospheric layers. It's beginning to build detailed pictures of what these worlds are like. One of JWST's early results was the detection of carbon dioxide in the atmosphere of a gas giant exoplanet. This was the first definitive detection of CO2 on an exoplanet, and it demonstrated JWST's capabilities. Since then, JWST has observed many more planets, including some super-Earths and mini-Neptunes, gradually expanding our understanding. What we're learning, climate and composition. From atmospheric studies, we're learning about exoplanet climates. Hot Jupiters, for instance, have very different climates on their day and night sides. The day side is intensely heated by the star, reaching temperatures of 1,000 to 3,000 degrees Celsius or more. The night side is cooler, But powerful winds transport heat from day to night, preventing the night side from dino freezing. These winds create complex weather patterns. There might be jet streams, storms, and turbulent mixing. Clouds of vaporized minerals might form on the day side and rain out on the night side. The atmosphere is dynamic, constantly churning and changing. For cooler planets, we're learning about water vapor content, cloud coverage, and greenhouse gas concentrations. These factors determine the planet's surface temperature and habitability. A planet with a thick CO2 atmosphere might experience a runaway greenhouse effect like Venus. A planet with less CO2 but abundant water vapor might have a temperate climate like Earth. Biosignatures. The search for life's chemical fingerprints. The ultimate goal of atmospheric characterization is to detect biosignatures, signs of life. Certain combinations of gases are produced by life and wouldn't persist in an atmosphere without life to replenish them. Oxygen is one such gas. Oxygen is reactive. It quickly combines with other elements, disappears from an atmosphere, unless something is constantly producing it. On Earth, that something is photosynthesis. Plants, algae, and cyanobacteria split water molecules, releasing oxygen into the atmosphere. Without life, so if we detect oxygen in an exoplanet's atmosphere, especially in combination with other gases like methane that are chemically incompatible with oxygen, it suggests life might be present. The combination of oxygen and methane is particularly compelling because on Earth, both gases are produced by life and they react with each other, so their coexistence requires continuous replenishment. Other biosignatures include phosphine, pH 3, which on Earth is produced primarily by microbes, and certain organic compounds that might indicate biological activity. But we need to be careful. Not all oxygen is biological in origin. Photodissociation of water vapor by ultraviolet light can produce oxygen, as can certain geological processes. False positives are possible. We need multiple lines of evidence, careful analysis, and skepticism before we can confidently claim detection of life. The pale blue dot revisited. What Earth looks like from afar. To calibrate our search for biosignatures, scientists have studied Earth as if it were an exoplanet. If aliens observed Earth from light years away, what would they see? They detect oxygen and methane in disequilibrium, a strong biosignature. They'd see water vapor, carbon dioxide, and ozone. They'd detect seasonal changes in atmospheric composition, particularly the increase in CO2 during winter, when plants in the northern hemisphere die back, and its decrease in summer, when plants grow vigorously. This seasonal variation is itself a biosignature, indicating a biosphere responding to changing sunlight. They'd also see the red edge, a sharp increase in reflectance at near-infrared wavelengths, caused by chlorophyll in plants. Vegetation absorbs red light for photosynthesis, but reflects near-infrared light, creating a distinctive spectral feature. By studying Earth as an exoplanet, we're learning what to look for on other worlds. We're building a template, a set of characteristics that indicate a living world, and then we're applying that template to the exoplanets we're observing, searching for matches, challenges, clouds, hazes, and interference. Clouds and hazes complicate atmospheric characterization. They're opaque, blocking our view of deeper atmospheric layers where interesting molecules might reside. Many exoplanets have thick clouds or photochemical hazes that obscure their atmospheres, making composition measurements difficult or impossible. This is frustrating. We can see that a planet has an atmosphere, but we can't see through it to determine its composition. It's like trying to read a book through frosted glass. Some planets have clearer atmospheres. Thankfully, These become priority targets because we can learn more from them. But many potentially interesting planets remain obscured, at least with current instruments. Future telescopes might use different techniques, observing at longer wavelengths, where clouds are less opaque, or observing the planet's emission rather than its transmission spectrum to peer through the clouds. But for now, clouds are a limitation. Temperature inversions and exotic chemistry. Some hot Jupiters have temperature inversions, where the upper atmosphere is hotter than the lower atmosphere. This is counterintuitive. Normally, atmospheres get cooler with altitude, but it can happen if there's a strong absorber in the upper atmosphere that traps heat. On some planets, that absorber might be titanium oxide or vanadium oxide, molecules that absorb visible light and convert it to heat. The presence of these molecules creates a stratosphere, a hot upper layer similar to Earth's stratosphere, which is heated by ozone absorbing ultraviolet light. These temperature inversions create interesting chemistry and dynamics. They affect cloud formation, wind patterns, and atmospheric circulation. They make hot Jupiters even more exotic than we initially thought. Water worlds and steamy atmospheres. Some super-Earths and mini-Neptunes might be water worlds, planets where water is abundant, perhaps making up a significant fraction of the planet's mass. These worlds might have deep oceans, possibly hundreds of kilometers deep, overlaid by thick, steamy atmospheres of water vapor. At the bottom of such oceans, pressure might be so high that water exists in exotic high-pressure ice forms. Even though the temperature is warm, the interior structure of these planets would be very different from Earth's, with layers of liquid water, high-pressure ice, and possibly a small rocky core. Detecting water worlds requires measuring atmospheric water vapor content and comparing it to models. If a planet has abundant water vapor and the right density, it might be a water world, but confirming this requires detailed observations and careful analysis. The next decade. What we'll learn over the next decade? JWST and other telescopes will observe hundreds of exoplanet atmospheres. We'll build a statistical understanding of atmospheric properties, which types of planets have clouds, which have clear skies, which have abundant water vapor, or carbon dioxide or methane. We'll study planets in habitable zones, looking for biosignatures. We'll probably find some ambiguous cases where the data suggests but doesn't prove life. And possibly, just possibly, we'll find a clear, unambiguous biosignature that strongly suggests life exists on another world. That discovery, if it comes, will be transformative. It will change humanity's perspective on our place in the universe. It will inspire new questions, new research, new missions. It will be a milestone, a turning point, a moment when we learn we're not alone. Or perhaps we won't find life. Perhaps we'll observe many planets and find no biosignatures. That, too, would be informative. It would tell us that life is rare, that Earth is special, that the conditions for life are more stringent than we thought. Either outcome advances our knowledge, either outcome matters. Patience and persistence. Atmospheric characterization requires patience. Each observation takes hours or days of telescope time. Analysis takes months. Confirmations and follow-ups take years. We're building our understanding slowly, data point by data point, planet by planet. But that's okay. Science has always required patience. We didn't learn about Earth's atmosphere in a day. We didn't understand our own planet's climate immediately. We studied it for centuries, gradually piecing together how it works. The same will be true for exoplanets. We'll study them for decades, maybe centuries, slowly learning their secrets, and each new discovery will be a gift, a piece of the puzzle falling into place. So let's be patient. Let's appreciate each new result, each new atmospheric detection, each new piece of understanding. Let's marvel at the fact that we can learn anything at all about worlds so far away. And let's keep searching, keep observing, keep wondering. Close your eyes. Imagine a telescope pointing at a distant star. Imagine starlight streaming through a planet's atmosphere, carrying with it chemical fingerprints. Imagine scientists analyzing that light, identifying molecules, building a picture of a world they'll never visit, but are coming to know intimately. That's what we're doing. That's the work. And it's beautiful, isn't it? The future, next generation telescopes and missions. We've accomplished so much in exoplanet science already, from 0 confirmed exoplanets in 1990 to over 5,000 today, from crude detections to detailed atmospheric characterization, from speculation to knowledge. But we're just getting started. The future of exoplanet science promises even more discoveries, even deeper understanding. Let's talk about what's coming, shall we? Let's explore the telescopes and missions that will shape the next chapter of this story. The Habitable Worlds Observatory, NASA's vision. NASA is planning a flagship mission called the Habitable Worlds Observatory, HWO, designed specifically to search for signs of life on exoplanets. It would be a large space telescope, possibly with a mirror 6 to 8 meters in diameter, optimized for direct imaging and spectroscopy of potentially habitable worlds. HWO would use a coronagraph or starshade to block the star's light, allowing it to directly image planets orbiting nearby stars. It would study their spectra, looking for biosignatures like oxygen, methane, water vapor, and other indicators of life. HWO is still in the planning stages. It probably won't launch until the 2040 seconds, but it represents the long-term vision for exoplanet science, not just finding planets, but characterizing them in detail and searching for life. Plato, Europe's planet hunter, the European Space Agency's PLATO, planetary transits, and oscillations of stars, mission is scheduled to launch in the late 2020 seconds. It will observe hundreds of thousands of stars, looking for transiting planets. Unlike Kepler, which stared at one patch of sky, Plato will observe multiple fields, eventually covering a large fraction of the sky. Plato's goal is to find Earth-sized planets in Earth-like orbits around Sun-like stars, true Earth analogues. It will observe each field for at least 2 years, long enough to detect planets with orbital periods up to about a year or slightly longer. Plato will also perform asteroseismology, studying stellar oscillations to determine the precise ages, masses, and sizes of stars. This will help us understand the planet's host stars better, which in turn helps us understand the planets themselves. Ariel, atmospheric remote sensing infrared exoplanet, large survey. Another ESA mission, Ariel, will launch in the late 2020 seconds, and as mission, focus on atmospheric characterization. It will observe about 1,000 exoplanets, studying their atmospheres in detail. It's designed to build a statistical understanding of atmospheric properties. How common are clouds? How does composition vary with planet size and temperature? What factors determine atmospheric chemistry? Ariel will observe in the infrared, where many important molecules have strong absorption features. It will study hot Jupiters, warm Neptunes, super-Earths, the extremely large telescopes, ground-based giants. On the ground, several extremely large telescopes are under construction or planned. The extremely large telescope, ELT, in Chile, will have a 39-meter primary mirror. The 30-meter telescope, TMT, in Hawaii, will have a 30-meter mirror. These are enormous instruments, far larger than any existing ground-based telescope. These telescopes will be able to directly image some exoplanets and study their atmospheres using high-resolution spectroscopy. They'll be particularly good at observing planets around nearby stars, complementing space-based observations Ground-based telescopes face challenges that space telescopes don't: primarily Earth's atmosphere, which blurs images and absorbs certain wavelengths of light. But they have advantages too. They're much cheaper than space telescopes, easier to maintain and upgrade, and can be built much larger. Adaptive optics systems can correct for atmospheric blurring, allowing ground-based telescopes to achieve remarkably sharp images. Combined with coronagraphs to block starlight, these telescopes will become powerful tools for exoplanet science, starshades, flying in formation. One proposed technology for direct imaging of exoplanets is the starshade, a large, flower-shaped screen that flies in formation with a space telescope, positioning itself between the telescope and the target star to block the star's light. Unlike a coronagraph, which is built into the telescope, a starshade is a separate spacecraft. It flies tens of thousands of kilometers away from the telescope, precisely aligned to cast a shadow on the telescope's mirror. This shadow blocks the star's light, while allowing the planet's light through. Starshades require extraordinary precision. The alignment must be accurate to within meters, over distances of tens of thousands of kilometers. But the concept has been tested and is feasible. A starshade mission could potentially discover and characterize dozens of Earth-like planets, searching for biosignatures, interstellar probes, the ultimate goal. Looking even further ahead, some visionaries are thinking about interstellar probes, spacecraft that could actually travel to nearby star systems and study their planets up close. The Breakthrough Starshot Initiative proposes using powerful lasers to accelerate tiny spacecraft to a significant fraction of light speed, allowing them to reach Proxima Centauri in just a few decades. These spacecraft would be small, just a few grams, but they could carry cameras and instruments to photograph planets and transmit data back to Earth. Such a mission is highly speculative and faces enormous technical challenges, but it's not impossible. And if we ever hope to study exoplanets in the kind of detail we study planets in our solar system, we'll need to send probes there. For now, that's a distant dream. But dreams have a way of becoming reality if we work toward them persistently enough. Artificial intelligence and machine learning, new tools for discovery, beyond hardware, new analysis techniques are accelerating exoplanet science. Machine learning algorithms can sift through vast amounts of data, identifying potential planet candidates more quickly and accurately than humans can. AI can help characterize atmospheres, classify planets, and even predict which systems are most likely to harbor life. These tools don't replace human scientists, but they augment them. They handle the tedious parts, sorting through mountains of data, identifying patterns, leaving humans to do what humans do best, asking questions, forming hypotheses, interpreting results, and wondering about what it all means. Collaborative science, a global endeavor. Exoplanet science is a collaborative, international endeavor. Telescopes in Chile, Hawaii, and space are operated by agencies in the US, Europe, and other countries. Data is shared openly. Discoveries are made by teams spanning continents. Scientists from around the world work together toward common goals. This cooperation is one of science's great strengths. We're not competing to hoard knowledge. We're collaborating to build it. We're pooling resources, sharing expertise, and working together to answer humanity's biggest questions. In a world often divided by politics and conflicts, science offers a model of cooperation. It shows what we can achieve when we work together towards shared goals. And exoplanet science, in particular, reminds us that we're all inhabitants of the same tiny planet, looking outward together at a vast universe that belongs to all of us. What we might learn over the coming decades will likely answer some profound questions. How common are Earth-like planets? Are we alone in the universe? Or is life abundant? What is the diversity of planetary systems, and how do they form and evolve? Can planets survive the deaths of their stars? Are there planets in orbits or configurations we haven't yet imagined? We might find biosignatures on multiple worlds, suggesting that life is common, or we might find none, suggesting that life is rare and precious. Either answer will shape our understanding of our place in the cosmos. We might discover planets so strange, so exotic, so different from anything we've conceived, that they force us to expand our definitions and theories. We might find water worlds, lava worlds, planets with multiple suns, planets orbiting dead stars, planets that defy categorization. The universe has surprised us at every turn. There's no reason to think the surprises will stop now. Hope and humility. As we look to the future, we should feel both hope and humility. Hope, because the tools and missions being developed will allow us to explore the universe in ways never before possible. We're on the cusp of answering questions that have tantalized humanity for millennia. And humility because the universe is vast and complex, and we're just beginning to understand it. We've found a few thousand planets out of the trillions that must exist in our galaxy alone. We've studied a tiny fraction of the cosmos. We know so little, really, but that's okay. Not knowing is the beginning of learning. Mystery is the fuel for curiosity. Wonder is the engine that drives science forward. So let's embrace our ignorance. Let's admit what we don't know, and then let's set about finding out, one observation at a time, one discovery at a time, one small step at a time. The future is bright, isn't it? Full of possibilities, full of promise, full of worlds waiting to be discovered and studied and understood. And we get to be part of it. We get to witness this golden age of exoplanet science unfold. That's a gift, a remarkable, precious gift. Close your eyes. Imagine the future. Imagine telescopes revealing dozens, then hundreds, then thousands of Earth-like worlds. Imagine atmospheric spectra showing clear biosignatures. Imagine humanity's perspective shifting as we realize we're part of a universe teeming with life. Or imagine the opposite, a universe where life is rare, where Earth is one of the few worlds where consciousness arose, where our responsibility to preserve and protect life is all the greater because it's so precious. Either future is profound, either future matters, and we're the generation that will start to learn which one we inhabit. That's extraordinary when you think about it. Philosophical reflections. What exoplanets mean for humanity. We've covered the science, the methods, the discoveries, the planets themselves. But let's step back now and think about what it all means. What do exoplanets tell us about ourselves? About our place in the universe? About our future? Let's get philosophical for a bit. Don't worry, we'll keep it gentle. No complex arguments or dense theories. Just some quiet reflection on the meaning of distant worlds. The Copernican principle, we are not special. For most of human history, we thought Earth was the center of the universe. Everything revolved around us, literally. The sun, moon, planets, and stars all circled Earth, or so we believed. Then Copernicus came along and showed that Earth orbits the sun, not the other way around. We weren't the center. We were one planet among several, circling a star. It was a demotion, in a sense. We were less special than we thought, but it was also liberating. If we're not the center of everything, we're free from that burden. We can see ourselves more clearly, understand our actual place in the cosmos. The discovery of exoplanets continues this Copernican revolution. Not only is Earth not the center of the solar system, our solar system isn't unique. Planets are common. They exist around most stars. We're one planetary system among billions in our galaxy alone. We're not special, and that's okay. In fact, it's wonderful. It means we're part of something larger, something vast and diverse and complex. We're participants in the universe's grand experiment with matter and energy and complexity, the mediocrity principle. If we're not special, life might be common. If Earth isn't special, If planetary systems like ours are common, then perhaps life is common too. This is called the mediocrity principle, the idea that Earth and humanity are typical, not exceptional. If life arose on Earth, and if the conditions that allowed life to arise are common, then life might have arisen on many other worlds. Perhaps the galaxy is full of microbial life, with complex life being rarer, but still present in many places. Perhaps intelligence has evolved elsewhere, and we're one of many species wandering about the universe. This is hopeful, isn't it? It suggests we're not alone. Somewhere out there, other organisms are living, growing, reproducing, evolving. Perhaps some are intelligent, asking the same questions we're asking, looking up at their own skies and wondering if anyone else is out there. The rare Earth hypothesis. Maybe we are special, after all, but there's a counter-argument. Maybe Earth is special. Maybe the combination of factors that allowed complex life to evolve here is rare. Maybe most planets are barren, and life-bearing worlds are few and far between. Consider all the things that had to go right for Earth to be habitable. We needed to be in the habitable zone. We needed a planet of the right size to hold onto an atmosphere. We needed plate tectonics to regulate climate. We needed a large moon to stabilize our axial tilt. We needed Jupiter to shield us from some asteroid impacts. We needed a stable star that doesn't flare too violently. Maybe all these factors together are uncommon. Maybe most planets lack one or more of them. Maybe life is rare, not because it can't arise, but because the conditions for it to arise and thrive are stringent. If that's true, then Earth is precious, rare, special in a way that demands care and respect. We might be one of the few oases of life in a vast, mostly lifeless desert of space, the anthropic principle. We're here because we can be. Here's a different angle. The anthropic principle suggests that we shouldn't be surprised to find ourselves on a habitable planet. Because if the planet weren't habitable, we wouldn't be here to observe it. It's a bit circular, but it makes a point. Out of all the planets in the galaxy, we find ourselves on one that's habitable. Why? Because only habitable planets can have observers. We're a selection effect. We observe a habitable planet, not because habitable planets are common, but because we can only exist on a habitable planet. This doesn't tell us how common habitable planets are. It just reminds us that our observations are biased by the fact that we exist. It's a humbling thought. We're here because the conditions allowed us to be here. If conditions were different, we wouldn't exist to wonder about them. We're products of our environment, shaped by it, dependent on it. The Fermi paradox. Where is everybody? If planets are common, and if life is common, and if some of that life is intelligent, then where is everybody? Why haven't we heard from alien civilizations? Why haven't we seen evidence of their existence? This is the Fermi paradox, named after physicist Enrico Fermi. The galaxy is billions of years old. Intelligent life, if it arise, might develop technology, explore space, even colonize other star systems. Given enough time, a single civilization could spread across the entire galaxy. So where are they? Maybe life is rarer than we think. Maybe intelligence is rare. Maybe intelligent civilizations destroy themselves before they can colonize space. Maybe they exist, but are too far away for us to detect. Maybe they're intentionally hiding. Maybe they visited Earth but left no traces. Maybe we're just not looking in the right way. The Fermi paradox is unresolved. It's a puzzle, a mystery, a question that hangs over the search for extraterrestrial life. The discovery of exoplanets adds urgency to this question. We're finding habitable worlds. So where is everybody? Cosmic loneliness and cosmic companionship. Thinking about exoplanets can evoke two seemingly opposite feelings. First, loneliness. The universe is so vast. Distances are so great. Even if life exists on nearby exoplanets, we might never be able to communicate with it. The speed of light is a hard limit. Proxima Centauri is 4.2 light-years away. A message sent there would take 4.2 years to arrive, and a reply would take another 4.2 years to return. That's a long time to wait for a conversation. For more distant stars, tens, hundreds, thousands of light-years away, communication becomes impractical or impossible. We're separated not just by space, but by time. We're isolated, each civilization confined to its own little bubble of space and time. But there's also companionship, even if we can't communicate. Knowing that life exists elsewhere is comforting. We're not alone. We're part of a cosmic community, even if we're too far apart to meet. We're fellow travelers on this journey through space and time. Each of us, evolving, exploring, wondering. Both feelings are valid. The universe can be both lonely and crowded, both isolating and connective. It depends on how you look at it. Our responsibility, caretakers of a rare biosphere, whether life is common or rare, we have a responsibility to the life that exists on Earth. Our planet is home to millions of species, each one the result of billions of years of evolution. Each one is unique, irreplaceable, valuable. We're the first species on Earth capable of understanding our place in the universe, capable of asking these big questions. And with that understanding comes responsibility. We can shape the future of life on Earth. We can protect it or destroy it. The discovery of exoplanets puts this in perspective. Earth is one of many worlds, but it's our world. It's the only one we have, the only one we can reach. It's precious, not because it's the center of the universe, but because it's our home. We should treat it with care. We should preserve its biodiversity. We should address climate change and pollution and habitat destruction, not just for our sake, but for the sake of all life that shares this planet with us. The long view. Humanity's future among the stars. Looking even further ahead, some people imagine a future where humanity spreads beyond Earth, colonizing other planets and becoming a multi-planetary species. This is speculative, of course. We don't yet have the technology, and there are enormous challenges, ethical, practical, logistical. But exoplanet discoveries make this vision seem a little more possible. There are worlds out there. Some might be habitable. Some might, one day, be home to humans or to life that originated on Earth. This isn't about abandoning Earth or escaping our problems here. It's about expanding the scope of life, ensuring that a single catastrophe can't wipe out everything we've built. It's about exploring, learning, growing as a species. Whether this future comes to pass or not, the discovery of exoplanets expands our sense of possibility. The universe is bigger and more diverse than we imagined. Our future might be too. Wonder as a moral good. Finally, let's talk about wonder. Exoplanets inspire wonder, a sense of awe at the scale and complexity of the universe. And wonder is valuable. It enriches our lives. It connects us to something larger than ourselves. It reminds us that there's always more to learn, more to explore, more to discover. In a world often focused on the immediate and the practical, wonder offers a different perspective. It encourages us to look up, to think big, to ask profound questions. It makes us better, in a way. So perhaps the most important thing exoplanets give us is not knowledge, but wonder. They remind us that the universe is vast and beautiful and full of mysteries. They remind us to be curious, to keep questioning, to never stop exploring. And that's a gift, a quiet, gentle, profound gift. Close your eyes one more time. Imagine the galaxy with its hundreds of billions of stars, each one potentially hosting planets. Imagine the diversity worlds of ice and fire, worlds of rock and water, worlds we can barely imagine. Imagine life arising on some of them, looking up at their own skies, asking their own questions. And then imagine yourself, here on Earth, part of this vast cosmic tapestry. You're made of stardust. Literally, the atoms in your body were forged in ancient stars. You're connected to the cosmos in a very real, physical way. You're part of something larger, and that's wonderful, isn't it? Closing sequence. What are exoplanets? It's the question that brought us here, whispered softly at the beginning, like a child, asking if there are other worlds in the sky. And after wandering through detection methods, hot Jupiters and super-Earths, habitable zones and atmospheric characterization, TRAPPIST-1's 7 siblings, and the search for Earth 2, we find ourselves gently circling back to where we began, still wondering. We've learned that exoplanets are common, far more common than anyone expected. We've explored how scientists find them using clever, indirect methods, watching for tiny wobbles and subtle dimmings. We've discovered that planetary diversity exceeds our imagination, with worlds ranging from scorching hot Jupiters to frozen ice giants, from rocky super-Earths to puffy mini-Neptunes, from worlds with 2 suns to worlds with none. We've learned that the habitable zone is not just about distance from a star, but about atmosphere and magnetic fields, geological activity, and orbital stability. We've seen that the TRAPPIST-1 system offers Hope's 7 rocky planets, 3 potentially habitable, all waiting to be studied. We've understood that characterizing atmospheres is possible, that we can read the chemical signatures of distant worlds, and perhaps, someday, detect signs of life. Maybe exoplanets don't have to answer all our questions to be valuable. Maybe they're meaningful simply for existing, for expanding our sense of the possible. Maybe that's the whole point. The universe doesn't need to provide easy answers. It simply exists, vast and diverse and mysterious, inviting us to explore it, one gentle discovery at a time. So, with all of this in mind, are you still awake? If you are, I hope it's not because I was too interesting. Though if I was, at least you've learned a few things about the thousands of worlds orbiting other stars along the way. And if you're already drifting off into dreamland, may your thoughts be filled with softly glowing suns and planets drifting peacefully through space. Before you drift off completely, I'd love to know where you're listening from and what time it is in your part of the world. Drop a comment and share. Are you perhaps an astronomy student pondering these distant worlds? Or someone who just finds exoplanets strangely relaxing? Maybe you're looking up at the night sky right now, wondering which stars have planets, which planets might harbor life. If you found this gentle journey into the worlds beyond our solar system relaxing or informative, or both, please do consider giving this video a like and subscribing to Sleepy Science Student. It's a small gesture that helps me keep bringing you more calming, curious content from the universe and beyond. Thank you for joining me on this journey through the cosmic neighborhood. Sleep well, dream deep, and may you wander peacefully among distant worlds in your dreams. Remember, right now, as you rest, hundreds of planets are crossing in front of their stars, creating tiny dips in starlight that telescopes on Earth are recording. The universe is constantly revealing itself, slowly and gently, one photon at a time. You just have to be patient enough to listen. Good night.